debugging the in-person version, Ian and Jeremy, I will tell you a little bit about why you should be interested in debugging the in-person version and what we're going to do with that. So this will be, if we designed a training like this, that I've been talking for like 25, 30 minutes, so everybody has time to debug and get up to speed with your homework. So this is a little introduction into the code, but also in general into dynamic rupture simulations. And after me, Marlon will back me up with a little one-on-one on what you actually need in practice to run models like this one that you see visualization here. This is actually our third training example today. So this is the dynamic rupture simulation of the core earthquake that hopefully will run on Frontera and on your laptops at home by the end of the morning session. Okay, so first, SeisSol is supported by a lot of projects and a large group. We were able to work almost 24 hours around the clock the last days because we're spread out across the West Coast in San Diego and Munich in Germany. And I want to acknowledge the support by a couple of European and German and US projects, specifically CHEESE, DT Geo, GeoInquire, and a few NSF funded projects. As I said in the introduction, I'm not a SCOPED PI, so I'm here as a fan and to contribute a little bit in terms of rupture dynamics. So far we have 65 plus contributors that have added to the code, and hopefully there will be more. And we have this little website, how to contribute. We can contribute as a user just by reporting issues or contribute as a developer. We have a discussion forum. Specifically, there's two different ways how you can bring up issues. You could open an issue or open a discussion. So an issue is really related to bug reports or things that should work but do not work. And the discussion is more related to ideas about maybe future things that could be added, or just to have a discussion about, for example, moving away from Fortran name lists. So by the way, there's no more Fortran in the SeisSol code base. We have T-shirts, or some of our students, they brought T-shirts that says now 100% performance and 0% Fortran, but it's a little bit sad. So for a long time we were, Oh, that was something related to our input files. But for a long time we had some of the physics parts still in Fortran, kind of a legacy, nostalgic reasons, but also for easier access. I wouldn't say for younger students, more like maybe for older faculty, but now at the moment, we don't have any Fortran left. So, but yeah, so this is kind of these two ways how you could bring up things. We do have a code of conduct. It's longer than this, but I just want to highlight that that if you start a discussion or you post an issue, you can be sure that that we try to demonstrate empathy and kindness, and there will be no bad feelings, or you will not be there will be no hopefully everybody will stick to the code of conduct and how these things are being handled. Okay, so you heard a lot about this, I assume already, in terms of computational seismology. So this is actually a global seismic wave propagation, which is a little bit different than what you've seen the days before, because as you can already see, the globe is discretized using triangles here, tetraheders in 3D. And that is one of the things what SeisSol is doing a little bit different. But in general, we are also solving the seismic wave equation. This is one of the reasons why I think computational seismology is really a pioneering field for HPC, because we're data rich and we often can solve our problems as a linear hyperbolic PDE, which has certain advantages in terms of efficiency. And today is all about HPC. So I think it's nice to think a little bit about why seismology is such a favorite application for high performance computing. And the key activities are calculation of synthetic seismograms in 3D Earth and solving seismic inverse problems. The common approach to do that, and that's actually a picture by April, who is not. Okay, but like now I have to update the reference. Okay, but the common approach is to do the time domain solution of space-dependent seismic wave fields solved by domain decomposition in space. So that means we're splitting up our computational volume into many small pieces and we distribute them across a large computer. And there's a lot of ongoing challenges, better accountants for 3D Earth or Mars structure on this picture, computational efficiency, complex geological subsurface, higher frequencies, and open community solutions, and SpecFam is the key example here. Now, there's a quote by John Trom, who basically said that the forward problem for seismic wave propagation is solved. So maybe we can discuss this over lunch if everyone agrees about this one. But it's certainly, I think, a little bit different if you're thinking about earthquake dynamics and how to treat the earthquake problem. So if you're thinking about earthquakes, but also other applications in engineering or in tsunami modeling, we often require not only extreme multi-scale approaches, but also multi-physics capabilities. And the examples that we will look at today, we have this multi-physics capability by nonlinear coupling the seismic wave propagation simulations with a spontaneously evolving frictional failure on these faults. So you're solving not only the wave equation, but you're nonlinear coupling it in a multi-physics way if you want with dynamic rupture, which is a frictional constitutive law that describes how the earthquake is unzipping these fault systems. And SeisSol, we don't talk about this today, but the SeisSol code can also model 3D coupled earthquake tsunami simulations. So you can couple the seismic wave propagation part with acoustic wave propagation and then gravity waves. So what you saw here in this animation is a single simulation that has rupture dynamics, seismic wave, acoustic waves, and a tsunami being generated by that earthquake. And there's another example that's called Palo in the SeisSol training repository. We don't have time to go through this today, but you can check this one out too. Okay, so as I just said, in these kind of models, we solve for spontaneous dynamic earthquake rupture as a nonlinear interaction of frictional failure and seismic wave propagation. And earthquakes are treated as frictional shear failure. So if you have some experience maybe with fracture mechanics or with engineering, where you're often interested in opening cracks, that's not what we do. We treat earthquakes only as shear motion. So either strike slip or dip slip, so mode 2 or mode 3 shear motion. So these are shear cracks. And these shear cracks evolve along pre-existing weak interfaces. So we have quite some meshing components in the training today, because one of the things that you have to be aware of is that we are prescribing the geologic faults. So we're prescribing these fault systems that can then fail spontaneously in these simulations. But we're using methods that are solving the seismic wave equation. So we're really bootstrapping on all of the developments in computational seismology. So it's the same, we're solving the wave equation everywhere in these models. It's just an additional multiphysics component that has the dynamic rupture part. This is kind of a typical overview of all of the initial conditions and the verification. So there's a lot of parts in these kind of models where we can include different kind of observations. And you can already see these are quite multi-scale. So we can, of course, include geological features. This is, for example, the Kakora fault system embedded in a 3D velocity model with topography. These friction laws that describe the dynamic rupture part are typically constrained by laboratory experiments. This is the one that you've seen there. This is a rotary shear apparatus. We have to think about the loading, the stress, initial stress conditions, the mesh generation part to put all of this information together. We solve the wave equation coupled to rupture dynamics, and then we generate a lot of output that can be synthetic seismograms, but it can also be, for example, ground deformation and other aspects. And by doing that in 3D, we can really directly integrate and interpret geophysical observations and all of these aspects to learn about fundamental physics, but also to talk to other communities. So, for example, this is a simulation where we were modeling earthquake bangs, so loud sounds that were observed from very small earthquakes, local magnitude 1.8, induced seismicity in Finland, in Helsinki, and the biggest concern from the population was that there was very loud rattles and sounds caused by these earthquakes. So this is actually a point source simulation with the seismic wave field and then an acoustic wave field of the small earthquake. Or we could link to tsunami models or to long-term geodynamic models to better understand subduction zone hazards. And there's a really nice paper we hear about later. Just want to highlight this. Sorry, building this up again. By Marlon, very big. And Marlon will explain all of this in a bit more detail when I'm finished. Okay, so as I said, we're treating earthquake dynamic rupture embedded into these wave propagation simulations. And we do this as a boundary condition in terms of contact and friction. So this is a thin fault. two matching fault surfaces that are in unilateral contact, and then there will be a displacement discontinuity across this fault, and that is the slip. So the displacement is caused by this earthquake. So the important part here is that everything the earthquake will be doing in your simulations is not predetermined. So that's part of the numerical simulation, but it's spontaneously evolving as a consequence of the initial conditions and the way the fault yields and slides. And that's controlled by the friction law that is relating the shear and the normal traction to the slip rates and the tractions that are developing on this fault. And there's different friction laws that you could think about. So these kind of methods have been implemented in various numerical schemes, from finite difference and finite element type methods. The first approach, or the first most common approach, is to split the fault interface, to use the split node approach. We're not doing that in our case. In our case, we are treating these boundary conditions with numerical fluxes. Since this is the discontinuous Galerkin method, as I explained in a little bit, that has some advantages, but also other disadvantages, especially in terms of computational cost. And of course, there's more to earthquakes than just what happens on the fault and in terms of seismic waves. There's much complexity that lives already in the definition of friction, but it's also really important to think about fault geometry, and we can also account for off-fault deformation. So what you see here is a comparison with observed fault zone width of the Landers earthquake. So this was compiled using optical pixel correlation. You have a high-resolution picture of the Landers area before and after the earthquake, and you can compare them, and then you can map out where there was a co-seismic deformation. And you can see that this accumulates around these areas where you have kind of bands or jumps between these fault segments. And you can also model that in terms of plastic strain induced by these very high stresses that evolve during earthquake rupture. One thing that you might notice, or that you will see when you're looking maybe through the material, is that these kind of earthquake rupture dynamic simulations can have a lot of complexity. So for example, just having a very simple model like this one in 2D, combining wave propagation with a rate and state-based friction law with fast velocity weakening, you get a full slew of rupture styles. You can have dying pulses, growing pulses, you can have cracks, and you can have very different rupture speeds going from subshear to super shear. So super shear earthquake is similar to maybe an airplane that goes through the wall of sound. So these earthquakes propagate faster than the S-wave speed of the surrounding material, and you can stack up S-waves and surface waves, exposing some areas that in the area of the MAC cones to larger ground shaking than a slower earthquake. So there's a whole slew of rupture styles that can be modeled with that. And one example is that we can try and understand slip reactivation. So the same fault can rupture multiple times during the same earthquake. So here's an inversion of the Toku earthquake, where you can see that during this, I don't know, 500 or 300 seconds of earthquake rupture, some parts of the fault ruptured multiple times. And that is actually something that we can understand from rupture dynamics, because if you have a pulse-like earthquake rupture, you reaccumulate stress at the hypercentric area, and you can slip again and again during the same earthquake. So it's just one example of what kind of complexity these models can try to explain. Okay, so it's the complex models, and we are striving to do this at the scale of real-world observations. And earthquakes can be quite large. So this is here a dynamic rupture model of the 2004 Sumatra earthquake. So the main fault that you see here of the megathrust plus displace altogether is 1,500 kilometers of rupture surface. So this is really large. This is almost from, I think, from Santiago to here. It's a very large model. And of course, you don't see that here, but you also have the seismic wave propagation part in that simulation. So there's a few challenges associated with that. These earthquake source processes are difficult to constrain because we can't measure them directly. They're also highly nonlinear. So this linking of rupture dynamics with wave propagation is a nonlinear process. So we have to think about, what of the physical processes is really important to include in these models to better understand the dynamics of field earthquakes. But that's maybe more of a challenge for today. How can we do that actually in a suitable manner for software and hardware that is utilizing what we know in terms of modern solvers and in terms of quite heterogeneous HPC systems, or even heterogeneous, Mac versus Intel architectures. And how can we lower the barrier for more people to do these kind of simulations? There's a really nice white paper by Nadia Lapusta. It was published in 2019, which is not only about dynamic rupture, but also about seismic cycle simulations, long-term earthquake simulations, so really quite comprehensive, that I'm linking on this slide, which has a lot of information too about how to include different observations in these models. Okay, so some challenges if we try to do this on exascale. We can maybe discuss this later. I'm not sure who of you is really interested in the very HPC aspect of this. But some of these methods we actually included in SeisSol, so we'll be using them if you want or not. So for example, we typically use code generation. So we're kind of taking over the job of the compiler because we actually know how our loops are structured. So we're generating hardware-specific assembly level code. We're also thinking a lot about load balancing and how to offload certain tasks in terms of to better address imbalances across large architectures. We think about optimized usage of memory and resiliency, which is very important if you're thinking about these largest machines available, because inevitably some cores will fail and cause nodes to crash. Okay. We've been using SeisSol to do a couple of recent earthquake simulations, or to better understand recent large earthquakes. So this is an example of the Ridgecrest, California sequence, where we've been modeling the 6.4 foreshock, and 34 hours later, the 7.1 main shock in linked models. So this is not a tool that allows you to do whole sequences of earthquakes and a seismic slip, but you can have multiple rupture dynamic simulations that are talking to each other. And I maybe don't go into too much detail here, but we've basically found that it's important to account for structure, so 3D velocity model, ambient long and short-term stresses, as well as the fault system interaction during earthquake rupture to really understand the complexity of these events. This is how the geometries can look like that we would like to include. So it's quite a complex 3D fault network that was hosting the Ridgecrest sequence. So the first event ruptured into this orbital fault system, which you can see here, and then the second event ruptured the main fault. We're also interested in including observational initial conditions that often in California they can come from community models. For example, a 3D community velocity model. There's a stress model, or you can think about the world stress map or other resources, how to get initial stresses into these simulations. And we've been also linking this to, as I just said, Coulomb stress models that can better constrain the conditions of this fault system just before the earthquake. This is how you could think about these two earthquakes talking to each other. So first of all, if you're modeling these two events in the resolution that at which we published that is around 10,000 CPU hours, which is not a whole lot for an HPC application. And you can look into things like what are the dynamic stresses, so the wave-induced stresses on the main fault that later hosted the main shock here. Can we understand why it didn't trigger this event immediately? And what are the static stresses caused by the displacement? And these are the kind of synthetics you could produce. You can, of course, compare what happens on the fault. You can also look into moment rate release that you can measure on the fault, compare this, for example, to back projection. You can check the fault surface offset during the simulation. You can look into static GPS and surface displacement compared to INSER or static GPS measurements or continuous GPS. Or, of course, velocity in terms of teleseismic or regional seismograms. And you could do this for, the foreshock and the main shock. And you can check what happens off fault, map out this off fault deformation, and then look, for example, into surface rupture mapping or damage proxy maps, and try to understand why we observed these kind of complex core seismic behavior. We also did that for the Turkey earthquakes, which were very devastating. As a reminder, it's more than 53,000 fatalities. So these models that you're seeing here were also the first earthquake and then the second event of the doublet. And I don't have too much time to talk about the science of this, but I'm happy to discuss it later. Okay, so what is the cost and why is today an HPC day? So if you are interested in modeling these larger earthquakes or models in very high resolution, for example, small events that have been recorded in the high frequency range, or broadband ground motion modeling, or if you really would like to include a lot of fault zone complexity, we do need HPC to run these simulations. And there's two ways or two kind of branches how we are engaging with HPC. So we routinely try to utilize full supercomputers for what you could call a hero run. So this is kind of a benchmark or trying to really utilize with an optimal performance full machines such as Frontera, for example, that you will use today too. So this code, SeisSol, is capable of scaling up to the full machine with quite good performance. But in practice, we typically don't do that. We have much smaller runs that allow us to explore the parameter space, for example. So the largest meshes we've been producing so far have 685 million elements. We also use high order accuracy. So that means that translates to 10 to the 12 degrees of freedom in terms of problem size, which is quite large. We also are thinking more about output size. So if you're looking at the 3D with seismic wave field, that can be easily tens of terabytes, even from small simulations. Reduction of that is possible, but limited. So we will see that we use modern data formats, for example, HDF5. We could write our output in single precision. We use file system aware sequential output. Or what we often do is that we only store 2D outputs. For example, what happens at the free surface, what happens on these fault surfaces, which reduces the output to 100 gigabyte or something like this. And that's quite challenging in terms of what was discussed on the first day in terms of fair data sharing standards, because if you're producing this large amount of data, it becomes tricky to archive that. And for example, if you're doing one of these hero runs, you would like to share this 3D wave field. This is, I think, a bit of an unsolved problem. Okay, so high resolution models, as I said, need HPC. So here's an example. If you would like to compute the Ridgecrest earthquake simulations up to 5 Hertz in the seismic wave propagation simulation part, for example, including a fault zone, what you can see there, and then look at fault zone effects in spectral acceleration. So that's more of a ground motion modeling or engineering study of interest, where in this study we've been showing that if you're including a fault zone in these models, spectral acceleration is actually affected all the way to the property. So it's not a pure source effect. So if you want to do this kind of models, you might need 9 hours and 400 nodes of, in this case, SuperMOOC NG. So that's around 170,000 CPU hours for this one simulation. If you get charged just for the energy, that could be $320. I think I'm out of date there. I don't know, Marine can correct me on this one, how much AWS would charge for 170,000 CPU hours, but probably impossible to run. And this is 2 barrels of oil or flying from London to Los Angeles. So there's a very strong motivation in terms of carbon, very strong motivation to optimize the software and also to fully utilize the output if you run such a simulation. And of course, that's machine dependent. So one way how to use all of the simulation output is that we could, this is a recent study where we've been looking into placing, in this case, 1.8 million virtual seismic stations to try and look at the spectral fingerprint of earthquake physics in near field data. And what you're seeing is corner frequency, but you can translate that into vertical acceleration surrounding this Ridgecrest simulation here. And you can see there's a lot of complexity that's linked to source effects. And that is just one example that we can use these models to better identify what to look for. For example, if we had a large array or a DAS data surrounding the Ridgecrest earthquakes here, we could try and hunt for these signatures of earthquake physics in spatially dense data. We can also use the output to come up with machine learning-based approaches or reduced order models. So this is a recent study where we've been using the results of data-intensive computation to construct reduced order models, preserving the low-dimensional information, in this case to evolve or to evaluate instantaneous shape maps, for example, for early warning or for probabilistic seismic hazard assessment. And again, please ask me about this if you're interested. We're currently extending that approach to time-dependent wave field simulations. So instead of using 250 CPU hours for this wave field simulation, we could evaluate that in a few milliseconds. Okay, so we're on the path to exascale supercomputing. I already mentioned that. So exascale means 10 to the 19 floating point operations per second. Given, of course, we have codes that probably address vectorization, maybe energy limits, all of the specialized hardware that's coming up, and how to optimally use the decrease per freedom in terms of accuracy. And we actually have 2 official exascale machines in the US at the moment. And we also have hope on observational side. So there's a couple of new dense earthquake observatories that already exist or that are being proposed. So there's a lot of new data that will be coming in, specifically in terms of geodesy. We're entering a golden age of geodetic imaging data in terms of the NISA mission. So there's a lot of new data that will be informing these models. Okay, so SeisSol that you will be using is open source, as I said, and a couple of details about that method. So we're solving the seismic wave equation using a discontinuous Galerkin approach. There's a specific time integrator that we're using that's called ADER, and we're using unstructured TET meshes. These TET meshes are specifically suited to represent complex geometry. So what you see there, for example, is the wave field of a point source in the volcano topography. And the reason for that is that it's easier to fit a triangle or a tetrahedron into these complicated shapes than to try and squint or match that with a hexaeder. We have quite heterogeneous media support, so elastic media, of course, and viscoelasticity for attenuation, fault zone viscoplasticity, anisotropy, and poroelasticity. And I add in percentage the kind of computational overhead that this will add to your simulation. So if you're adding poroelasticity, that is about 360% increase in computational costs. But anisotropy is for free, and adding upward plasticity is almost at no cost. We have this multiphysics coupling. We talk about dynamic rupture today, but as I said, we also have implementations for tsunami in the same code to understand the earthquake-tsunami interaction, and for elastic acoustic wave interaction and so on. It's a high-order accurate code, not only in space, but also in time. So it's not only the spatial discretization that is high-order accurate, but also the time integration. And it's suitable for high resolution since we're parallelizing. So SeisSol is not the only DG method, of course, for wave propagation. I add a couple of other papers here. And one example is the speed code. It's being developed for engineering applications in Milano, but there's other ones there too. Okay, so in summary, it's or the short version, it's a software that allows for rapid setup of models with realistic non-planar intersecting fault systems and complicated topography with high order. And it's more expensive than a finite difference method, for example, but these extra flops in terms of storage or time to solution can be performed fast, exploiting HPC in computational science. Here's an example from the speed code that I just mentioned. Okay, so we use unstructured TET meshes, high order accuracy, as I just said. You will also see that the meshes don't have the same size. So we use spatial adaptivity. We're zooming into regions that are more interesting than other ones with smaller elements. And we also use the same method for seismic cycling simulations, but that is another topic. Okay, so why would you use DG? DG allows for low numerical dispersion. Minor changes include dynamic rupture. The faults can intersect and branch. ADA, this is the motivation for higher order accuracy in time. This can be done cheap with this method if you do it correctly in terms of hardware optimization. Our demotivated tetraheders, it's really beneficial for very complicated geometries or intersecting surfaces, and for this kind of coarsening and adaptivity. I don't know if you're interested in that, but if you have a DG method, you can choose the kind of numerical flux that is used to communicate between elements. There's different ways how to do that. You can have nodal implementations or modal implementations. Modal means that the fluxes are being exchanged between element interfaces. So there's some advantages to that too, and also to the choice of basis functions that we're using. So this is a bit of a history of SeisSol. I said we started with something that I call a geophysics version. So there was a Fortran 90 code parallelized with MPI, and it's writing text files and reading text files. And from that, we went to compete for the Gordon Bell Prize, which is something like the Oscar for computer science in 2014. We did that with a scenario of the Landers earthquake, which was quite a big setup at that time because we wanted to resolve up to 10 Hertz. And these were the optimizations that we developed for that. So we changed the hybrid MPI and OpenMP. We changed the data formats to be parallel, use parallel I/O, so HDF5. We had this offload scheme for putting some of the more expensive calculations on the accelerators at that time, into Mike specifically, if you're interested in that. But the main part is this assembler level, the G kernel. So that's what I tried to explain before, is that we do our own, we're kind of taking over the job of the compiler for that part. And that allowed to preach to this 1 petaflop per second performance barrier for SuperMove for the first time at this point. But in terms from the user perspective, it allowed us to have not only 10 times faster time to solution, but to run 100 times bigger problems. So what Marine just said is that often in practice, you're actually restricted by the size of the problems that you're able to run, either by the ball clock time on your machine or by not having access to a large computer. So this kind of optimization allows you, even on a smaller location, to just run much bigger and more interesting problems. And this is a little explanation about what this code generation means. So we're automatically detecting and exploiting sparse sparsity patterns in our matrix operations. Maybe I talk about this if you're interested. I can talk about this more later. In 2017, again, for the supercomputing conference, we set up this scenario of the Sumatra earthquake. As you can see, in terms of problem size, the decrease of freedom, it's not such a big increase, but it's many, many more time steps. So 3.3 million time steps compared to 200,000. And the reason for that is that we changed our time stepping scheme to be local, to involve a local time stepping scheme. So that means that not every element is updating at the same speed, with the same time step. But if you have small elements that are ill-shaped, that need more updates to remain stable, they can do that. And larger elements that are better shaped, they can just update more sparsely. And there's a big optimization gain, but it also allows us to handle meshes that are not optimal. The kind of screwed up meshes, bad quality meshes. This can be very nicely mitigated with that optimization approach. And a few words about SeisSol today, the version that you will be using. So on CPUs, we have this MPI OpenMP pthread hybrid parallelization scheme. So we're parallelizing, over some of the parts of the problem with OpenMP. And on GPUs, we employ CUDA, HIP, or SiCL for all of these small matrix multiplications, depending on the vendor or the hardware that you're using. So we have support for AMD, NVIDIA, and Intel. We're still porting some of the rheologies to GPUs. I have this on the next slide. The details are here if you're interested specifically about the GPU optimization, because that's something we spent a lot of effort on in the last years. I want to highlight for those that are not interested in dynamic rupture, you will still be interested in what we're presenting today. So we have this kinematic source example, and also we have support for full physics-based anisotropy, the full triclinic anisotropic materials, and the reference is up there. This is been worked by Sebastian Love. And for poroelasticity, it's really interesting. We're seeing, for example, really interesting effects close to interfaces that haven't been reported before. So that is something just from the wave propagation part of these things. And it would be interesting to optimize these kind of rheologies too. Okay, so the grand challenge of meshing, since we will look into meshing in almost all of the examples, there's currently, I would say, 2 community standards, hexahedral meshes. If you want to include dynamic rupture in them, that can require a lot of time, and you have some limitations in terms of geometries. One common tool is Trellis. I don't know if they changed their name again, but you probably know what I mean. The second community standard, I would say, is unstructured TED meshes, so what SeisSol is using. It's easier to have fully automatic meshing workflows. However, you can have challenges in terms of badly shaped elements that then, if you have a global time stepping scheme that really restricts your time step to small sizes to remain stable. That's typically what's called a sliver element. This is one of the problems you can have. And we will use GMSH for more complex mesh problems. We also use SimModeler, which is free for academic use in an academic spin-off company. There's other approaches, curvilinear meshes. So here's, for example, SW4 that allows you to account for topography by, using this curvilinear meshing approach. We experimented with that as well. So that is something you don't have to mesh beforehand, but the code will take care of that for you. You could also think in terms of rupture or crack models, the multiphysics in terms of diffuse interfaces. So you can have phase field-based models that describe this. So you can see that these kind of cracks that are modeled here, they were not meshed before the simulation started. But we will today use mostly GMSH, which is free. It's capable or very capable to mesh most simple geometries and everyday mesh sizes. There's many tutorials online. It's a little bit limited in terms of geometry, specifically for intersecting faults. For that, we use SimModeler, but we don't have a tutorial about that today. And the mesh is provided in a parallel data format, and SeisSol will do the internal partitioning, so you don't have to worry about that, how to distribute the mesh across the multiple nodes or cores that you're using. I wanted to show, as I said, there can be meshing problems. These sliver elements, you might have heard that, but here's an example of how this actually looks like. You can see that they're in red. So you have this really bad aspect ratio. So one side of the element is very short compared to the other sides. And that's just at the intersection of a shallowly dipping subduction interface with a free surface. So the impact of such a sliver element, did you talk about this? Okay, so you're running your wave, you're solving the wave equation, and it takes a long time. And why it takes a long time typically is that you have to make sure that you're solving or your solver remains stable. And there's actually a condition if you use an explicit time integration, what most of us will do for hyperbolic PDE. It's called a CFL condition. And that links the cost of your simulation to the mesh size, to the wave speed. So that's why if you're looking into slower wave speeds like sediments or something, that's why simulation gets more expensive. And if you have a badly shaped element, the cost of your simulation, because of this criterion, will go up. Also, if you include slower wave speeds, the cost of your simulation will go up. And the runtime of your simulation is directly proportional to 1 over the minimum time step that you need to update your solution to remain stable. So one bad element can make your full simulation even computationally infeasible if you are using a global time stepping scheme. So what we are doing is local time stepping. Each element updates with its own time step. And that is something that you will use when you're doing these examples. And there's a theoretical speed up that you can gain with this. But yeah, we're not the only ones that do that. There's actually a spectral implementation by Max Friedman of that, but I don't know if that's in the version you've been using. Maybe not. Okay, and since it's a HPC day, here's a scaling plot. Basically, what this shows you is how the time of your simulation is going down when you use more nodes. So this is one of the things we're trying to achieve is this has a nice linear slope. If you have the same problem, you run it on 128 nodes versus 6,144 nodes. You would like to get almost, you know, one-to-one faster with a linear slope. Okay, and for visualization, we use ParaView. We talk a little bit about this later. I think this is probably all I have. There's a couple of more visualizations. Maybe I skip through this and go to the summary. Okay, so these are the three examples that we go through. A very simple dipping normal fault in a reduction scenario. Then we have a kinematic earthquake source simulation of topography, and then the Crack 4 earthquake. Couple of the points that I talked about, but in this point, we can have questions, and then Marlon will talk about the dynamic rupture model one. Any questions? Does it work now for everyone? Yeah? So these simulations are what we showed today is really focused on large dynamics. So very simulations where you don't describe what happens to trying to understand the physics. For point source, I don't know. I would say our niche is more in the multiphysics part, but we can discuss this later. Just continue together. Run simulations both for point source or the final effects, like addressing the kinematic ruptures, but not the dynamic. These dynamic rupture simulations are more to understand the evolution. But and typically yeah. We also don't have any global seismic wave propagation applications. It gets very expensive if you would like to do that on a global scale. So if you're producing global seismograms, we often use other tools, InstaSeis in our case, or Spectrum or something like this. So it just doesn't pay off for global simulations. Mm-hmm.
I have a question about uncertainty. So when it comes to dynamic rupture, say the pure wave propagation, where do you see the largest sources of uncertainty? Maybe they're capturing the crustal properties or capturing the frictional physics. And then the second question is, where are the biggest challenges in introducing these uncertainties in those?
Okay, so we do have it's a good question. So typically what you see if you have these kind of expensive forward models is that you can't do more than sensitivity analysis by, for example, running, I don't know, tens of simulations, varying the fault geometry, varying the crustal properties, and then trying to understand if this really has an effect of the observations you have. But we are at the verge of being able to do that more systematically. We have dynamic source inversion, so we're actually using, I don't know, MCMC approach to invert for the physical parameters on the fault. And we're also looking into combining this with UQ methods to get a better handle on this. So this is exactly where we can only get to because of the forward models becoming cheaper, more optimized. Because if you can only afford running 10 or 20 models, this becomes it becomes difficult. We just start with doing that systematically. You want to take over, Marlon? Sorry. Yeah, any questions about the Fonterra part? Well, I'm looking for Marlon's presentation. Let me just download it. Yeah, get a coffee, it's 10 while I'm setting up. I only have downloaded the PDF, so I'm trying to get the PTX. Okay, got it. Actually,
And then,
okay, should we do a 5-minute break?
Yeah.
And start at 10 past again? I don't know if you have presenter notes, but it would be here.
oh,
You don't?
no.
Okay. I actually also have this. I didn't use it, but I do have this.
Oh, yeah. I feel like sometimes you can see it, sometimes you can't.
Yeah.
Yeah.
How are you doing?
Well, yeah.
I have a paper track with me that I want to show
You do, okay, 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 yeah, yeah, I wanted to help you too.
Yes.
So I know like competed in Finland, so one
Yeah.
is working with for explosions, more often interested into the acoustic response, especially when you know,
Did you see the paper? Yes. Yeah. Just mute. Okay, welcome back. It's my pleasure to introduce Marlon Ramos, who worked extensively with SeisSol during his PhD, and he's now a research geophysicist at Sandia National Lab. Right?
Yep.
You're starting.
All right.
Thank you, Marlon.
Yep. Thanks, Elise. So today I'll be giving more of a simplistic view of all that goes into a dynamic earthquake rupture simulation. And as was mentioned, I'm currently a research geophysicist at Sandia National Labs, where I don't work on earthquake problems anymore, but more explosion problems as well as distributed acoustic sensing.
Oh no, but then it's not good because then you see this. 1 second. Yeah. Sorry. Doesn't work. What is use slideshow? What's that? What happens? Ah.
Thank you.
All right. So I typically would start this talk about why do we model earthquakes, but I think everyone that's attending here has good reasons for doing so. And so just touch basically how do we model earthquakes? We've seen before that we can look at simple point sources. In this case, you can specify a moment tensor or looking at the stress tensor itself. And these tensor components are not functions of time. The earthquake just happens, and that's related to point source dislocation theory. And then we solve the wave equation as normal. We can also look at things kinematically, where these are typically done through slip inversions, where you have slip on the fault, and then when you make assumptions for your Green's function, you can propagate that disturbance to get the elastic wave field. And then, as Elise noted, you can also look at the dynamic source itself, which in this case, the outcome is not predetermined. You need to specify sort of the laws of physics that's occurring on the fault. So a friction law that is coupled to your hyperbolic PDE for the wave equation itself. And this is an example from the Guerrero subduction zone where you're looking at slow slip and it's coupled to dynamic rupture. So you could see how all of these ingredients evolve through time and sort of uncover temporal dependent processes during earthquakes. And so, on this note of how do we model earthquakes, a seminal paper in 2002 was by Madariaga and Olsen looking at earthquake dynamics. So sort of laying down the foundational equations of fracture mechanics and sort of the theory and looking at applications for what then was how the state of the art, how do you model these multi-physics sort of simulations? And when I finished my PhD, I realized that that was a great paper that got me started, but there's just been so much literature. There's been so much that's been written since then, as well as our computational resources have really burgeoned, especially now in the field of big data and HPC. And so I took it upon myself to write this guide for people who are interested in these dynamic models, but also for maybe the non-expert who really wants to see what's going on under the hood. And just really serve as a brain dump from my PhD advisor, and as well as what Elise has taught me through my PhD. And so for this talk, I'm just going to briefly go over some of the main points of what you might want to keep in mind when designing a dynamic earthquake rupture simulation from first principles. And so this is more of a fleshed out chart of sort of what is the big picture that you're looking at, as well as what are the different ingredients that go into a dynamic rupture model. So you want to keep in mind about the dimensionality of your problem, 2D, 3D, that will impact your computational cost, as well as what type of mesh you might want to use. And then another thing you want to keep in mind is numerical convergence of your model. And I'll touch down touch base on this towards the end of how we can sort of infer that our simulation is well resolved. And the inputs to dynamic rupture, look at the geometry, your fault friction law. You want to look at fault stress and strength. So initial shear stress, effective normal stress, and then your frictional parameters. And then the properties of the earth itself. So what is your velocity model? And then are you looking at elastic, elastoplastic, or perfect plastic sort of behavior for those rocks at your time scale of interest? And then when you actually run the dynamic earthquake rupture code, you also want to be worried about or keeping in mind, how are you going to make it start? So we call this nucleation. And that's typically accomplished by using a time weakening or a overstressed patch or asperity to sort of start that earthquake. And I'm sure as Elise is motivated a lot, you can look at these dynamic ruptures papers or studies to look at specific earthquakes, or to look at parameters to sort of understand what are your limitations or constraints, and how does that affect the wave field or surface displacement, or even tsunamis. And this is a list of some of the dynamic rupture codes that are available to us. Here we'll be going through SeisSol, which uses a high order spectral element method, discontinuous Galerkin method. But there's many that use finite differences, finite elements, or spectral element methods. And this is a nice paper compiled by Ruth Harris et al. In 2018 that was looking at the SCEC benchmark results for all of these. And so you have the code type and the references, and then how you can sort of get it. Some are open source, some are maybe not. So the first thing I always sort of think about is, what is the dimension of your problem that you're looking at? So in 2 dimensions, you can look at either mode 2 or mode 3. These are conventions adopted from fracture mechanics, where mode 2 refers to an in-plane crack. That's sort of figure A here, where you can look at a strike slip fault or a dip slip fault. And so this typically elicits P and SV wave radiations. You can also look at mode 3, so sort of anti-plane rupture. Here in the middle figure, I have a strike slip fault. So this might be common in a more cycle simulation, where you're just taking a cross section through maybe like the San Andreas. And mode 1 is typically just an opening tensile crack that's typically not addressed in dynamic rupture codes explicitly, but it can happen theoretically. And of course, when we move to 3D, you have a mixture of both modes. So both mode 2 and mode 3 sort of cracks as you're growing the rupture front now, which now has a surface area instead of just along one single dimension. The input geometry, if you're going fully complex in 3D, you have to worry about topography as well as the fault surface. And typically you'll download like a structural model or a lat long file using for the topography or your fault trace, and you have to discretize that somehow. And these can have millions and millions of unstructured elements here. This is an example for the Landers earthquake that was done in 2018, which incorporated a depth-dependent velocity model, all fault plasticity, as well as all of this different heterogeneity and non-planar fault geometries. And sort of your tools to mesh, it can be SimModeler, PumGen, or GMSH. Not open source, Trellis or Qubit. And I think as many of us in the room can appreciate, just like when you first learn to code, you're self-taught. And so when you're designing finite element meshes, it can be really difficult when you're starting out. And so you really want to work with someone who has that expertise. And luckily the SeisSol group does have that. So that's a great thing to have. And so one of the ways that dynamic rupture models are different from kinematic rupture models is that it has a friction law. And this is coupled to your elastodynamic equations of motion. And in dynamic rupture problems, you'll have 2 main friction laws used, linear slip weakening on on my left here, or velocity weakening. And slip weakening means that the fault slip as it evolves locally only depends on a few parameters, so not the slip rate, just simply slip. And it's characterized by this parameter called d sub c, which is the critical slip weakening distance, and that's intimately tied to how much available you have for fracture energy. If you consider a simple energy balance of the earthquake process, and the lower two plots here show how they are related in terms of stress. So you can have friction coefficients on the top or stress on the bottom, and the velocity weakening is similar, but it also has a lake scale, but also introduces parameters A and B, which are adopted from rate and state frictional processes. And I've highlighted just two general equations illustrating how the friction coefficient will evolve at a place on the fault through time based off these two friction laws we think are applicable to the real Earth. And this neglects effects of cohesion, which you can also incorporate into these equations. You can have more complicated frictional laws, such as thermal pressurization, flash heating, or you can look at different types of dynamic models that implement a more classical rate and state friction formulation. But once again, it all comes down to what are you trying to either reproduce through observations, or what are you trying to study through a parameter, vary your parameters. And then, sort of what are the implications for the friction model that you might use? This plot shows three different simple 2D dynamic rupture simulations where you have an expanding crack, a self-healing pulse, and a super shear daughter crack here that's emerging. So, there's a bifurcation on the rupture front here, and the colors denote the slip rate. So the earthquake initiates at x equals 0 in this position along strike here. And the main difference between them is what is the rupture front doing immediately behind itself. So in the expanding crack, you sort of have a slip velocity that's it's quite large even behind the rupture front. But then the self-healing pulse, you don't really have that. You have healing. And when you have a super shear rupture, you have very high slip velocities everywhere. And that's born or seen clearly in this classic paper in Heat in 1990, where if you have a pulse-like rupture mode, you have healing behind the rupture front. So as the rupture is propagating, your slip velocity is sort of going to 0 or very minimum, as well as your stresses are. Whereas in a crack-like rupture mode, you won't have that sort of behavior. You'll just always have something unzipping, and you can get a mixture of these going on that's modulated by either your material properties or by the inertia from the wave field itself. So you could sort of start out as a crack-like rupture, but then you can evolve pulse-like, and just sort of what are the complexities that you have going on as a function of geometry. I'm going to skip this. This is earthquake energy budget. Showing radiated energy and fracture energies and how that can be related. But one of the main ingredients here for dynamic rupture models is what is the stress field? What is the stress on your fault? Stress in terms of what is the shear stress? And then what is your effective normal stress? And that can also incorporate pore fluid pressure. This is an example from Ulrich et al. In 2022, as well as Madden et al. 2022, where they looked at the Sumatra megathrust event. And here you have information on the directions of the least and most compressive principal stresses, denoted by sigma 3 and sigma 1. And so you could always rotate and resolve that onto your fault to sort of get a pre-stress that's going to be conducive to initiating dynamic rupture, and that can be expressed as the relative pre-stress ratio R, which this is the initial shear stress. If I'm reading the numerator, initial shear stress minus your dynamic fault strength. Dynamic fault strength is the product of your dynamic friction and effective normal stress, and divided by the difference in static and dynamic friction coefficient times your effective normal stress. So this might be, this could also be likened to the stress drop, or the strength drop, excuse me. So you can sort of see what areas are more conducive to faulting, or maybe might inhibit rupture propagation, Setting these initial conditions at a dynamic rupture, you can also look at what is the stress before and after your earthquake. So I took from this paper and Madden et al. You could look at the bottom plot, which shows sort of the different maximum principal stresses before and after an earthquake. So this is just a cross section on the Sumatra megathrust to show how dynamic rupture can also predict what your stress state might be following a large earthquake. Another popular approach for stress fields is actually using constraints from GNSS geodesy. So for megathrusts where we don't have seismic observations such as Cascadia, in 2021, I designed several rupture models that use geodetic coupling models to constrain the initial shear stress. And this is also called the complete stress drop assumption, where you take a slip deficit model and you calculate that expected stress change, and then you add that to the dynamic fault strength to inform that initial shear stress condition. And in this case, if you assume that everything was released in 1700 from Cascadia, you get a very, very large earthquake that sort of ruptures the entire megathrust and creates huge subsidence plots where we have offshore. And I didn't allude to this or mention this for the sake of time, but you could also set stochastic stress fields. You could also inform your stress field from different cycle modeling. So that'll set a new initial condition, sort of coupling that with tsunamis. And so it can get really complicated, but these are just two main ways that can be accomplished. And then how do you start your earthquake? Also called nucleation. I like this cartoon figure that was made in 2018 by sort of the two sort of end members of how we think earthquakes interact. Sort of is there stochastic sort of random little stresses that are going off and then sort of cascades and starts into a larger earthquake? Or do you have sort of deterministic or gradual stress build up on a fault where you can think of this sort of slow slip, and that might load a different section of the fault that's frictionally conducive to supporting rupture. And so what we do in dynamic rupture simulations is we have to force rupture to start at a particular time, but also keep in mind the temporal component as well. So how long is this going to last? And so what we'll typically do is define a critical length scale. This is called the critical half crack length. So if you look at this analytical expression, it's actually intimately related to your fault stresses, fault strength, as well as that critical slip weakening distance. You could derive these in 2D or 3D. You have to make many simplifying assumptions, so ignoring heterogeneities, and also thinking about uniform sort of stress conditions, at least where the earthquake is starting. And so you could derive this analytic expression. There have been many papers that have been published that explore what is the effect of changing this nucleation size as a function of your numerical method. A nice paper by Gallus et al. In 2015 that looks at it with SeisSol. And then what you want in nucleation is you want a rupture that is sort of, I guess, well sustained. That's going to, after you turn off sort of this numerical aspect of it, the rupture will evolve naturally, and you don't have any singularities or irregularities in that. And the two main strategies you sort of have for doing this is sort of time weakening, which recognizes that finite length scale. But then after a certain time, that rupture should evolve naturally, and you no longer have to have those stress conditions. You could also look at overstressed patch, in which case you just have the shear stress that's only slightly above your static fault strength, and so that provides enough stress drop to start the rupture. And as I mentioned before, if you don't do this properly, you can bias your model results. You can get a very large earthquake where maybe you don't want to, or some of the other dynamic processes such as off-fault heterogeneity or stress conditions are not going to be seen because you put too much energy in the rupture initially. And another last important point to keep in mind is how do you ensure that your model is well resolved? For elastic wave propagation, we can look at the velocity model, we can look at the elements. themselves as in the numerical method and sort of look at that. But for dynamic rupture problems, one of the things that we can also look at is something called the cohesive zone, also known as the process zone. And in this part, it's where it's the portion immediately behind the fault plane where you have shear stress decreasing from its static value to its dynamic value. That's represented schematically right there. And in here, you can have stress varying really dramatically, and you really want to resolve this sort of where this is occurring as a function of slip. And so this also depends on your numerical method. If you use finite differences, spectral elements, how is that going to change? These equations show n sub c is how many sort of elements are sort of sampling that process zone. And I also have a general expression for that process zone too. And this also changes with time. So you can resolve sort of what it is initially given your initial conditions, but due to inertia and other dynamic effects, this will change, this will contract as the earthquake is happening. And so you really want to resolve this and look at this process zone, not only theoretically, but also looking at it with increased mesh resolution and different time stepping methods. And this is sort of a fundamental length scale for dynamic rupture problems. And I wanted to conclude with a list of dynamic rupture papers, but I didn't have enough time. But hopefully the guide I wrote has enough of that. So you can look at the literature of what's been done, sort of where this field is heading. So thank you. Yeah.
Any questions, Amara?
Thank you, Marlon, for this presentation. I was wondering, because of your current work, if you have any comments about how to model dynamic simulation, let's say for an explosive source, because it's difficult for me in rock propagation, such a scenario. Probably bias, but for me, it's easy to imagine a moment tensor representation.
Yeah.
Rather than, so are you aware if there's any work related with explosive source simulations and dynamically, or if it doesn't make sense at all?
It does, but in that field, right, we typically rely on hydrodynamic codes. So you want to incorporate melting, you want to incorporate sort of different types of physics. But a lot of the things were the rheology of the medium, looking at these multi-physics simulations can be the same. It also depends on where you're observing. You can also use point sources to approximate that as well.
Yeah.
Thank you.
But very similar physics, you know, or similar problems.
Come on.
Are there any papers with how the learnings from the like the time like what changes learnings from like explorers or research studies deciding the dynamic co-simulation code, like maybe simulating and putting that has already occurred and comparing the results of the simulation application and trying to see like where the code is, where the mistake is it the low frequency, is it the high frequency, that's
Yeah, there have been studies. So I think about like in 3D, I know SeisSol has explored the Landers earthquake, so 1992. So there are reported seismograms. So trying to match them and what frequency.
Yeah, we did that for a few real earthquakes.
Yeah.
So Landers, Ridgecrest, the Turkey events, Palu. Yes, we should. I will put some papers in the Slack channel to have your list of papers.
Yeah.
Yeah.
Oh, one more question.
Do any of these models account for the activation of faults?
Activation.
Yes.
Yes, I think so, yeah.
I will share references maybe in Slack. So we want to get you working. So let's start with that. So Jamin, do you want to unmute yourself?
Yes.
Okay. You could share your video too.
Yep.
Let's see.
So now is like also instructing the in-person user after. So is there anyone that haven't finished this step? So you should follow the Slack channel for the most update instructions. Does anyone haven't finished this step? Please raise your hand and we will come and help you. Okay.
On.
Please note that instruction is actually very different than one is followed.
Yeah, so don't follow anything in the GitHub repository. Follow everything in the Slack channel over here. Yes. Sorry for the confusion.
Okay, only one person.
Yes. Yeah. You want to go? Oh, Ian can go to help. Don't be shy. Okay. Yeah. Yes. And in the meantime, we can take coffee right now.
Yeah, maybe we take 5 minutes to fix these 3 people I think I saw, and then we start with the first dynamic capture model.
Yes.
Yeah.
So if you finish this, you can also continue with the following. So
those that finished can start with that.
yes.
Yeah. I just invite on Slack.
For the online user, you can just start the Docker and the Jupyter Notebook, and if you can start the Jupyter Notebook, then we will in the same pace right now. Yes. So I can demonstrate how to do the VNC right now. So first, you go to the web page. I can share this. And is everyone going to here? So here is the TACC portal that very useful and very advanced compared to other supercomputer centers. Very useful. So you choose Frontera and you choose the VNC remote desktop. So we are connecting to the supercomputer through a remote desktop. And then the project is this project, and here is development. And the name, you can name whatever you want. Here I use the SeisSol training. And then you can click submit once you fill out all the things. Then we do screen cap. Here and into the back channel. Submit. Oh. use ENC to do the job. Don't use it in the origin. So you go to the So from here you can see now it's working. So you can see the section running and you click on it. Should I exit from well, you know, we can be there. It's fine. Yeah. So Oh, that one. Oh, I isn't it one? I yeah, so you need to make sure they actually exit I get one. Yes, yes. So, so you should stop the interactive part if you're using it. So let me show you. So from here, you can see the current job only should have one thing. If you see AI def, like other thing from there, you should end it.
Yeah, well, so basically we reserve 50 nodes, which is enough for each of these events. So make sure they're all using one node.
Yes. So you will see something here. So now you are in the Frontera remote desktop. Okay. Oh, sure. You can hit the something else. Yeah.
Close that out.
Yeah. So thank you. So what you do, I'm glad you made it here. You want the kids, you know, it's people in the side. I got it. Yeah.
If you issues of VNC, make sure you load the profit model, which is that in
It's in the
Oh, it's in the curtains?
Yeah, you wrote that one, that's like the. Like, reservation has to be with you for the home, but everything is.
So once you're in the VNC, you can open a terminal by right click and then open terminal. Then now you're actually in the desktop, which is not good. So you go back to your home. And you got all the stuff that we prepared just now. And then you can source this file. Yes. So here to set up the environment so that you can run through everything.
Make sure you terminate the other job. You want to go to the VNC, okay? I see some of your jobs actually pending just because we have another job. You can have one job at a time. Okay.
And then you can see the last line over here. You can just type the same thing.
So what we'll be doing is running these Jupyter notebooks on Frontera to get a nice interactive notebook on the supercomputer. And you need to be in CPU to forward that screen on that visual output to the laptop. And then if everything works, it will look something like this. So you get the Jupyter Lab view, and then you can, go to the SeisSol training and you get the notebooks.
And now this will be this will be the same with as a remote participant.
Yes, that's great for all participants and you can have the same screen. So that's task 0. Start the SeisSol trading on Frontera. I think it's too fast.
Yeah. Does anyone successfully open the Jupyter notebook in Frontera? Okay, not yet. Okay, well.
I still see some of your jobs pending because of the iPad designing. Make sure you ask it now. Oh, that's amazing. So that we can ask.
Should we copy the commands into GitLab? We can do that already.
Yeah, I should replace this in here. Yeah. Just copy and paste in VNC somewhere. Yeah, but I find out. So I'll share it. So you can see the link in here in the Slack channel and copy here. Okay, cool. And maybe you can start introducing TV.
Okay. Okay, Jeremy's going around and I will talk at the same time for those that already have it. Yeah, you just, once you're on a remote desktop, navigate to home, SeisSol training, then copy. You basically follow this CP command there, then source. And so it's 3 commands that you need to run once you navigated to home, SeisSol training. CP, source, and then the SWP command.
Oh, this is a new slide. The one that-
Yes, it was just updated. You need to follow this. Yeah, so follow what's here. So navigate to home SeisSol training, CP, as it says here. And that's also, the command is also on Slack. Then source, and then SWP. And what should happen is that you have a remote, nice Jupyter lab server that will serve for all of the examples that we have.
Okay.
And that will look the same. That will look the same after the training. You don't have access to Frontera anymore, but you can use the Docker images we have for, SeisSol to go on your laptops. But it will get you the same Jupyter lab framework where you can run these notebooks. So that will be the same. It's just that if you're running on Frontera, you have a little bit more power and you also get some exposure to an actual supercomputer. But it will be the same later on when you do that at home. It's a bit easier actually at home because you just get a notebook server. So those that are here, it's been actually also really tricky for us to set this up on Frontera. So this is why there's last minute updates. It's really not that easy to have them in HPC code being run from a Jupyter notebook on a supercomputer. A little bit new time. Yes. Oh, this is just the exact job. That's fine. Not one process. You're running them.
So that's not.
Five more minutes and then we go to the notebook.
Yeah, it's supposed to be a set of
R, sorry. Okay, so for remote participants, it's much easier. If you have a trouble, please post in the Slack channel or in a Zoom chat. So this example, I just start explaining it a little bit. It's one of the many community benchmark setups that are kind of increasing in complexity. So TPV means that problem version. So this is that problem version 13. It's a 3D setup of a dipping fault, a normal faulting earthquake. You see this little patch here. So this is the radiation patch that Mona just talked about. We're initiating this earthquake. And what you will see is that this earthquake breaks through all of the fault, causes static displacement, but also seismic waves propagating away from it. And there's a couple of additional complexities here. So this is actually a problem with off-fault plasticity. It uses linear slip weakening friction, but it has strongly super shear rupture conditions. So that's actually one of these earthquakes that will go super shear. So it will propagate faster than the S wave speed of the surrounding rock. So the earthquake itself will rupture quicker than the S wave speed. There's many of these benchmarks, as I just said, simple strike slip setups, like the problem version 5. There's some setups that have highly heterogeneous initial stresses. There's a branching fault setup, and so on. And to go through these benchmark exercises is one of the nice ways how to familiarize yourself with the complexities of these kind of models. And there's a link to the benchmarks at the bottom of this slide. Okay, and this is the one that we are going through. So normal faulting, dipping fault, strongly super shear kind of setup. And here is one of the, these benchmark setups are good for training, but they also really help the community to make sure that all of these different calls that exist are producing the same results. So this is one of these comparisons where you see the slip rate, so how quickly one point on this fault is moving during the simulation. You can see this is quite complicated. The earthquake starts with a very rapid increase of motion, and then it kind of comes out here. And you see there's different faults, Highland, for example, a couple of finite elements, vector element, and the G codes here being compared and producing very similar results. Oops. Okay. So the goal of this example was really to look into this physics-based prediction of time series of ground shaking. Specifically in this case, we were interested in, what are the near source shaking effects for engineering or hazard assessment. And of course, you will also understand earthquake physics, hopefully, when you're looking at this. Okay. As I said, we also included some meshing tutorials in these exercises because it's such an important part of setting up these models. So we will use GMSH in this example. So it's open source, also includes some simple geometry support. And that is actually task 1. So if you manage task 0, you have the notebook running on Frontera in your case. The next task will be to produce your first unstructured tetrahedral finite element mesh using GMSH or GMesh. Okay, so how this works in GMSH is that you always go from points, prescribing the points that you need for your model, to the lines, to the connections, connecting these lines, to surface meshes, to volume meshes. And GMSH has a perfectly user interface, so it looks something like this, or you can use scripts to build the mesh. And what we've provided is a very simple script, so that has a geo ending in the repository. And this is what's explained in the notebook. So we use the open source software GMesh for mesh generation, and we need these following steps. So we need a half space, so there's a free surface, box-shaped domain. We need to have our 60-degree dipping fault plane, and we need to make sure that we have our nucleation patch in there. There's reasons for that that are explained in these papers. And we need to set all our required boundary conditions. So GMesh comes with its own scripting language. There's lots of manuals and tutorial examples. It's a really good tool to get to familiarize yourself with, also for other tools. For example, PyLab is also supporting GMesh. But the first step is to specify the geometry. That's often called a CAD model. And the meshing itself is then done automatically. You don't have to do much. So where you really, as a user, have to do something is to specify where's the free surface, how big is our model domain, where's the fault, and where's the nucleation. So the script to generate that mesh is called tbv13training.geo. And just as a note, this is relatively small, the mesh that we will produce. So it will also run on your laptop or on one core of Frontera. But you can later like really change the resolution easily by yourself. Okay. So these are the commands for remote participants, very easy. You really just say gmesh, 3 is for 3 dimension, tbv13 training. On Frontera, we will run this command, and Jeremy, is this still up to date on the slides, or was there something changed? Are you busy helping for the GMS H1? I think this is up to date. So this is the first task. And you will see in the geo file, you know, you'll be prescribing the fault length, the fault width, and the dip angle that's bolded here. You also have like the maximum element size, how small the elements should be, 750 meters on the fault. And you have these kind of the fault dimensions here. So it's pretty simple. All of these geometrical coordinates. And these are the points that are specifying the surface here. Then you're prescribing the fault and the little nucleation patch with all of these points. And at the end, you will also have to describe the boundary conditions of the free surface, of the fault, and of absorbing boundaries. And in SeisSol, we're just tagging them. The free surface is 101, the fault is 103, and absorbing boundaries are 105. And what will happen then is at the end that gmesh is generating this mesh for you. It will also have some coarsening if you look at it in ParaView. And that is a really nice example.
Oh, you can come here.
Hmm?
You can go ahead and stop them.
Okay, so task 1 is the mesh generation following the notebook. Is this up to date?
Yes.
Okay. Mhm. Okay, we will copy and paste the commands in the Slack channel. So this is really useful, independent of any kind of model forward simulations that you're doing to get some familiarization with gmesh.
There's a way to do it. I guess.
So this
Maybe. Yeah, I'm used to it.
What I'm trying to do is add nodes.
Oh, it's also the word. So I did it wrong.
Yeah.
Well, it was good. In the, no. Okay, I'll see.
Really start on Ontario and always try the local installation that we provided.
I don't think, I'm not related to this.
Yeah.
Although there is one thing that I changed, but not really this band, it copies the setup into the direction. And then I couldn't find it here, so instead I copied it. So I don't know if that.
Yeah, it seems like I'm not like right. Personally, I would say. Okay, if you're stuck on with the first task on Frontera, try to change your line tree to this command. So first MPI run, Singularity run, my training SIF, Gmesh, and then all of the other things. You're running this from the notebook.
Doesn't think they actually. Yeah, you have to get rid of the dash and one. Yeah. But. Flat right now. Still have the problem. Yeah. You also have to make the same, yes. At the same time, beginning. Actually, I wish the first one copy and pasted, but the second one, I just said it's like, I'm not having luck with copies. I think you could use the right click to copy with it. Yeah, it wasn't word. Because I guess you're technically copying from one. It works like promoting like. Yeah. I think what's funny to me is how slow the interfaces that are supposedly on a supercomputer. Yeah, it's just like a latency. Yeah. But it's still funny to have such a slow interface.
Okay, let's go through this notebook. Does everybody is able to see the notebook at least? I mean, everybody passed task 0. Okay, so I suggest we go through the notebook for the in-person attendees and we just check if all of these commands are running for everyone. So we did some updates, but it seems like they were not completely passed through.
Yes.
Okay, so for the first one, because as I said, it's kind of an intertwined setup. So we're running from the notebook server on Frontera. So what should be put here is MPI run, singularity run, ~mytraining.sif.
And from there, you place it.
And you paste it in here. remove one of the exclamation marks.
You have to.
Yeah.
Exclamation.
So let's just go through this one by one for every of these cells. So this is the mesh generation part. It's basically using GMSH, reading this training script. You can look at it, it's quite simple. And then it's meshing first the curves, and then it will mesh the surfaces, and then it will mesh the volume. So that's really just part of the meshing setup. So any question? Can you go back to the first line?
First slide.
Yes. No, to what you just did.
Oh,
So everybody can follow. Okay, so that would be the first task. Can I see some hands if this works? You're first meshing? Wonderful. Okay, after this one. Oh, and by the way, if you're fed up with trying this, you can always install your local one, the version that you can take home, and that should work. I didn't see any complaints. Second one. Now, what we're doing
doing the same thing.
is we use a punch-in tool for the mesh generation, which is SeisSol. So this is one of our own meshing tools that we developed. There's a lot of documentation there that you can see. Again, we're adapting the command because now we're running within as I said, it's complicated. So it should be MPI run, singularity, run, my training SF, punch-in, -s, MSH2, TPV13, training MSH. So this is a parallel mesh generation now. But this is a library for efficiently generating large meshes. Should be very quick. Okay, so now we're just making the mesh ready for SeisSol. Can I see some hands if this works? Okay. Now in the next step, now we generated two files, an H5 file that has a H5 ending and an XCMF file. So they're both describing this mesh using parallel file format. In the next step, we're using PyVista, which is just a Python tool for visualization, and we look at the mesh. We have to
Takes a
change
while.
anything here? Probably
No,
not. Hopefully not.
You don't need to change anything here.
Okay. So you can just run this without changing anything. And then what you see is this visualization of the mesh that you just generated. Okay, so it's a box. You can see that it's statically refined, so you have much smaller elements where the action will happen at default, and bigger elements away from it. And the last part of that notebook will be to run the actual simulation. So that will be then, oh, sorry, you can go through changing some of these options, but maybe in the scope of time, we just run the simulation now.
This is running. Up. Sorry, I'm just finding it.
Maybe you can paste it in Slack too.
Yes.
Okay, so in this cell, we're running a simulation. And you can see a lot of output being generated. And this will run for a little while.
Actually, finish.
Oh, it's already finished?
Yes.
Okay. And then we can again use the notebook to look at the output.
Oh, it's very fast.
Yes. So what we're doing now is, for simplicity, we only look at what happened on the earthquake fault. And then we have different fields. So what you see here is this the slip rate, so how fast this is rupturing in dip direction. You can choose, you can see there's a lot of different fields that we're typically interested in. This is the traction along strike, and the documentation for what these variables mean is linked in the notebook. And so that is a 3D dynamic rupture example, and it's pretty quick to run, even on your laptops later when you do that. looks something like this.
Go to Northridge for the all 9.
Mhm.
This is just more visualization.
Mhm. Okay, and there's a couple of little exercises in this notebook looking at the parameter files and so on, but that's the simplest model to run. So that if you're completely stuck with Montero, I suggest that you run it locally on your laptops using the remote options.
Yeah, we have that role in this.
We can solve some more problems over lunch. We're not getting to our examples otherwise. You can start with the which one.
Okay.
You can do the same, just stepping through.
Yep.
Okay. So I suggest we go ahead and we show you the second example, which is not dynamic rupture, which is finite source with topography. It's maybe a little bit, yeah, it's also quite interesting. So this is the Northridge notebook, and there's also a slide deck associated with that. Maybe you can start with the slides.
Okay. Yeah.
And then we do the same. We just go to every command that has to be updated because somehow our Docker didn't upgrade in time for this training. Okay.
So in this example, we use the Northridge. We especially using the finite fault model as the prescribed kinematics on the fault surface, and then we can generate the seismic waves. So SeisSol definitely is solving the seismic waves too. So from here, the left-hand side shows one of the example finite fault models we use. So this is some steep distribution, and then we prescribe the steep evolution in each fault patch, and then we can generate the seismic waves from it. So the Northridge happened in 1994, is in the Los Angeles basin, so it has a very strong impact to the local community, and it surprisingly have a very strong striking. It turned out because a very thrusting fault, and there is a strong directivity towards the city over there. So you can see there's a lot of damaging towards Los Angeles County or city over there. So you can see what's going on over here. Interestingly, the Northridge earthquake doesn't happen in the St. Andreas main fault. There's a lot of spray fault or compressed fault geometry within the California. So there is actually a transverse hidden fault over there and rupture in that day. So the earthquake is magnitude 6.7 and the depth is around 18.2 kilometers. So it's a very shallow earthquake. And the rupture duration is around 10 to 20 seconds over here. So here is showing the moment tensor of this earthquake. So you can see there's a thrusting earthquake. And then we will use this kinematic model to generate the seismic waves And then in here, the demonstration, we will show you how we incorporate the final fault model and then to show the waveforms from the simulation output. So we use a standard format of the final fault model. There's many different formats. Specifically, we use this standard rupture format. So we prescribe every point in the final fault model by these parameters. We have lat long depth, strike, deep area, start time of the slip rate, and each duration of these pulses. So we, for example, here you can see we describe every time step by 0.2 seconds with the slip rate function. And you can see the first slip at this first time window, the second slip in the second time window, and describing the whole final fault model over here. So we have a streamlined program that can take this format and then to generate all the synthetic seismograms or ground shaking from these final fault models. If you use one support patch, that become a point source.
It's just a big collection of point sources that are overprinting, that are interacting to describe this finite fault model. Ordinary rupture, lots of point sources.
Yes.
Double castle point source. And the standard rupture format is nice because you can download a lot of these kinematic sources from some kind of task with breaks in USGS or from other platforms.
So we have this tutorial example in the same directory SeisSol training, and you can see the Northridge, and then you can click this Jupyter notebook. So for the online users, remote participant, you can just run through the whole notebook. It should work properly. So the first one, we generate more complicated mesh. So you can see now we have this surface topography. Previously, we only have a flat surface, which is a box. So here is just to show you how we incorporate some Python script to get this topography data and incorporate to Gmesh and then to create it. So in this Python, you can just run it. And we can download some topography data. And
so these scripts are quite complicated, but so it hasn't been possible to account for topography with GMSH since I mean it only became available I think 2 years ago or something. And the script here is really nice because we also are downloading the data and then you automatically produce the mesh with topography. So it's hopefully useful if you want to do that later. So that's quite a new feature. And also maybe one note, what we're also doing is we're projecting to a Cartesian coordinate system. So this is not latitude, longitude based, but we're already using the projection to build a Cartesian box, a rectangular box, not platform based. And as you can see, there's very little user interaction, so we just run to generate a mesh here.
So here we use the Gmesh Python API. So Gmesh can use in the command line and also in the Python over here. And then whenever you see this MPI run for Frontera user, then you have to use the container to run this PumpJet over here. Yep, you can. So we have set up the modules for you, so you should be able to import Gmesh. Or we can go through the whole notebook first. So here from the Gmesh, we create the same format. You can see there's mesh northridge.msh. So we have to use the PumpJet to create this high performance. You can parallel this meshes. So you can see we have like 3,400 cell size of this simulation. So this is just the same. We prescribe this finite form model, and then we prescribe the steep distribution and also the source time function. So this is what actually look like in the
Each of these dots is a small point source.
yeah. So we have very, very dense point source over there.
How big is the section that you show there?
So this is a 20 times 25 kilometer planar fault, 40-degree deep plane. It's a magnitude 6-ish, so it's yeah, that size.
One of the advantages if you're translating the finite source model into such dense grid of moment tensors, you don't get any artifacts. You don't have to put in size sequence. So if you use too few moment tensors, you get this kind of jagging behavior and a lot of artifacts. No, that's not important to use translate them using a lot of noise.
So the densification is it's not actually related to SeisSol. So we have the in-house Python programming so that we can upscale the model. Yeah. So here is what is actually doing. So you can see we're reading the finite form model in the standard rupture format, and then we will generate a format that SeisSol can read, which is a regular grid format that describes deep sleep, strike sleep, the sleep rate function.
Even if the source model that you download has maybe quite large discretization, we're resampling it to be highly enough sampled to give you a nice synthetic set.
So now we run the SeisSol simulation here. So you can see Frontera is very, very fast because the SeisSol is very fast. On Frontera, if the compared to the, so here we can finish the job within like 2 minutes. If you use your local computer, it may take 30 minutes or yeah, or more over here. So you can see SeisSol. Goodbye.
I just opened the order now. It says that that's not.
I can help you cite it later. Okay, yeah.
I have.
I think Carlos is saying
That's the library of. Yesterday.
The first one?
Yeah. The first one,
Yeah.
Yeah, this is the Python API. That's fine. Yeah, you have to use the phone.
Yes, this is it.
Oh, this is not.
I think it's empty around one.
Sure, the chord sound, I think.
Yep.
Yes, the last one.
So while debugging, I would quickly go through the third example, and then I can help you afterwards. So the third one is running the fully dynamic rupture simulation. So the previous one is you prescribe the fault with the kinematics, you prescribe the sleep, the moment, and now it's completely the output is actually the kinematics. You don't prescribe the input for it. So this earthquake is very significant. Here, just show you one of the faults graph in the New Zealand. You can see this. There's a 3.5 meter uplift in one of the fault over here. And very interestingly, this earthquake doesn't rupture one fault. So on the right-hand side, yeah, shows you the inside images. You can see the deformation field is very wide. It's not typically you can see one extra fault, one fault over here. And left-hand side just show you the map of the surface outcrop of the fault geometry over here. And the red one is the fault traces that occur during the Kaikoura. So this fault trace behind shows one of the unmapped fault over here. And you can see there's very complicated surface deformation of these earthquakes, which challenge our conventional view that earthquakes may be only happening in the single fault, relatively simple geometry. If we have complex fault, maybe it cannot run over here. So there are many final fault models of this earthquake. Here shows one of the final fault inversion. So to have a good match of the waveform, they have to have this very complicated fault geometry. I'm amazed at how complicated they put in. They must have put a lot of effort on prescribing, for example, there's more than 10 subfaults in this final fault model. And one interesting debate about this earthquake is actually there's a subduction zone beneath all this crustal fault. So you can see there's a large fault over here, which actually kind of prescribing what the megathrust looks like over here. So this kinematic model shows there is sleep over there, but we don't understand like why the rupture can propagate from this hypocenter and jump over different faults. What is the dynamic mechanism over this? So we have created these models in SeisSol. So here is why the discontinuous Galerkin method works, because we can prescribe this complex fault geometry with fault interactions. And then you can see we have created many complicated fault following the surface traces and also different data set. So we have this different over here. And the color over here is talking about the stress. So the input of this direct simulation is the stress. So you can see that there is from the surface to the depth, there is the seismogenic width. So within the seismogenic depth, we think is locked during the interseismic period and the stress is loading. And at the deeper depth, because you have the aseismic creeping during the interseismic sleep, so we will transfer some stress at the down dip over here. So with this model, we can actually reproduce a realistic earthquake rupture of the Kaikoura earthquake. So here is just a better illustration of how we create this compressed fault geometry. So in addition to the compressed fault geometry, we also use the topography. So you can see we overlay the topography over there and also use a 3D velocity model over there. So the plane cut is showing the slice of the 3D velocity model. And to reproduce this earthquake, we have to resolving the process zones that's just Ramos, Marlon described. So we have very fine resolution or meshing size on the fault everywhere. So you can see this earthquake is like tens of kilometers, 100 kilometers. And then we can only available if we have a large mesh. So we have a 29 million elements and we can resolve up to 3 Hertz near the fault, not the entire model domain, but only near the fault. So modeling the high frequency waves is still a very challenging problem. So now is the mesh visualization. In here, we already create the mesh for you because it's complicated. You cannot use Gmesh to do that. So similarly, we go to the Kaikoura super notebook. It's the same introduction that I just shared. So to create this complicated geometry, if you're from more like energy, engineering side, you know the CAD model. So we also the Pumgen and also the meshing also compatible with the CAD model, so you can do union, cutting, and merging or smoothing of the mesh geometry. And this is one of the snapshot of the wave propagation of the earthquake rupture. So there's a minor typo here. You add the scalars equals to elevation, and here just to visualize the mesh. So you can see we already created a mesh in the tutorial. It takes some time. It's huge.
Why did you add scalars?
Oh, because previously it only output like the partition number, so you don't have the color of the topography. So now you see over here. So actually, if you have good eyes, you can see there is some more refinement. The topography looks better near here, which is the rupture, and here is coarsening outside. So we have this adaptive mesh that yes. So PY Vista is also a very helpful tool to visualize all this meshing. Like Matplotlib can plot scalar variables, but to render this view, PY Vista is very useful. Yeah, but it's very painful to use it. So yeah. Yes, it takes some time. It's huge. If you want to see the edge, so here you don't see the edge of the mesh. You can replace this show at false equals to true, and you can see how dense the mesh is. You can try it, but I wouldn't try it here now. Okay, try it. Okay. Oh yeah, there you go. So you can see we have a refined mesh so dense that you cannot see the fault surface over here. Show edge to true, yeah. And now you can see within this area, we can refine the wave frequency higher because you have a denser mesh. The outside rupture, and maybe you cannot resolve it there. So we can have this gradation meshing. Yes. Oh, you mean the bottom one?
Again, we have to change that.
Yes.
So.
Yes, I will put it on Slack.
Changing the notebook run through the container. If you get stuck somewhere, please also write on Slack because there's a couple of people that are helping on Slack.
So now you can see it start the fault output, the start of the service output, and then it started running for the simulation.
What's simulation running? So this is the biggest. It's running. Okay. I'm very happy to hear that.
Yeah, this should be the easiest one because the mesh is already compiled. So
could you try that one? Because this one has already the mesh, so you don't get stuck if GMSH doesn't load. Could you try and run the Kakao example? This is also the most interesting one.
yeah, the most interesting one.
I mean, it would be good to have some core earthquakes here.
And then just to let you know the runtime for this one, I did it yesterday. So you can see using the supercomputer is relatively fast, 20 minutes. But if you use the laptop, then it takes 2 hours to run it. And this is already a downscale problem because we're using the tutorial. In the real life, we have to run it for like hours in HPC full scale. Yeah.
We also provided, like if it doesn't run, we provided the simulation output I can paste the link on Slack.
Yes.
So you can just download it if you want.
Yes.
So
Yeah.
I can paste. Oh, okay.
Oh, as soon as SeisSol.
Oh, that's good.
Oh, wow, it's very fast. Faster than mine. That means it worked.
That means
Goodbye means it's good. Yeah. It's some stuff. Yeah. How many knobs do you use? Do you use 10 knobs?
Yeah, I'm usually soon.
So the simulation runs, now you can see it runs to 40.2 seconds. Simulation we have is 30 seconds, so it's halfway there right now. And from the output, you can already see once the earthquake starts. So you can see it increase a little bit faster. The earthquake is propagating around the large area. So this is clear moment and time field increasing. Anyone have a question? S. Oh, so that's good. S. Okay, perfect. So after you finish running, after the finish running, you can check out the output there. Yes. How long does yours take? It's still running. So around 5 to 10 minutes.
Information about projection.
Oh.
So very soon. Oh. That depends on what you see. It's never been.
It's almost there. Yeah, no, we should be trying to because one low 26 volts. That's HPC Frontera specific. So you're not optimizing the RAM. Yeah, you can do that. these are optimized and it's machine specific. Yeah. So here I show you there's other way to visualize the output. So if anyone used Paraview before, nice. So you can use Paraview here in the VNC server. So you start a new terminal and you source. Oh, and you go to the home directory first. And you source the setup again. So what the source do is actually loading all the modules that need to run the Paraview and also the Python in the Frontera. Yes. Yes. It's like conda install, but it's already pre-compiled in the supercomputer, but it's not in your terminal. Yeah.
Yes.
So the key thing here is you type the SWR -E1 Paraview. No, you don't need to kill job. Yes. Yeah, because we are using it in the same VNC server. The whole job is one job of the VNC server. Yeah. So you see the Paraview. So yes. No worries.
So it's a new terminal, then you source the Frontera modules, and then it's SWR -E1 Paraview.
It's the same. You just switch from Julia to Paraview.
Yeah.
Yeah. Just enable you to do the visualization. Without that, you cannot run it over there. So for the remote participant, you have to open the Paraview locally in your computer to do the same thing.
From the incidents, I thought just like seconds, typically how many seconds modeling, and you see the time set as well.
So in practical, usually I run 1 second simulation and compute how many time it takes for 1 second. And if the whole simulation, for example, what I'm doing is 2-minute simulation, then I times 120. And you get the first estimate how much it takes. Yeah. So in Paraview, then you can see the output of, for example, the TPV13. You can see the output, and you see that the XDMF file. So there's different output. There's fault output, XDMF. Is everyone opening Paraview right now? If you can you raise hand? If you can, yeah. So and you.
So be able to look at some of the things that you know. No, like you said,
Yeah. So apart from the fault, you can also see the surface actually. And then you can also open the Kaikoa once it's finished. So you can see there's a complex fault of the Kaikoa.
Yeah.
It's still both the wave view and the rocker together. So this is changing the colors and grades. I can show the slides.
Yeah. Maybe.
So you can see exactly So for example, in here, you can see there's a hair wheel. And you see the fault over here. So this button shows the variable. So we have the absolute slip. So you can see the time is 0 now. So there's no slip there. If you select the final one, then you can see there's some slip over there. So ASI is not good for wave field. ASI is the absolute slip. So if you want to see the wave field, it's better to plot the slip rate. Yes. So you can also see the surface over here. So from the surface, you can see there's displacement field, and velocity field. So now you can see there is the wave field propagating over here.
This is what, if you look at the free surface, this is how the wave field looks like, this complex source. And if you look at the faults, you see the earthquakes jumping from second to second.
Yes, and here just to make you see the like.
One out, that's what you have. Surface, one more happens along the surface.
So you can change the time. Yeah. And
This example only works for everyone. Most complex only works.
yeah. So you can actually click the play button, and you can see every time step. So you can see the wave propagating outwards, yeah, from the source.
Can you raise your hand if you're still interested in some help? So take this last example. Go ahead.
Now it's very.
Any more? I want to see them more.
Yeah, from I asked this guy this for his you guys. It's the whole I think it's more likely that California's. Yeah. But I think California, I mean, oh, yeah. I think, no, I don't know, big California, I've heard like. You know something. I know. You really know. I know. Yeah, and it's not just a weird. Yeah, true. So like. Oh, I'm in back today. A lot. I went back like. That's, you gotta be really into it. Yeah, that's, I was gauging over. I don't, so, I grew up. Oh, so you probably saw that. Yeah. They said. Yeah. No, you gotta be a part of the board to sort of networks. Yeah. Like, I mean, just, yeah. Yeah. I mean, the it's scary, but it's. I think the thing about these is that you don't really have control over where the other. What are they like? Yeah, but the funds are kind of set up so that it'll take, we'll drag them out. You just go to the side and move that and the currents. Right. All written currents are water. You know, yeah. It's like. Yeah, so instill it in our. And it's. Yeah, I'm the white one. Yeah. Although like some way there, instead of like rolling, it may even start water. We don't think it's like white water is all day. But you might be able to get like half. Yeah. 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 It depends on the scale. So, I'm looking at like, different scales. So like asymptotic, right? So if you want to look at currents that are added, very slowly. Right. Maybe different seasons, like, and also like, what a wave waves around. But those are all different kinds of products. Right, so like over the constant setting, the rotation of the earth matters, right? But for a wave traveling across the ocean, rotation of the earth. It depends on the entity, sorry. Waves are, I think different. Yeah, I can tell. This like where I'm on. The force that adding, like So you can't pop it. So elastically, your first all. You do this thing where you basically expand it. You're gonna get a display type of experience. And you only take the first. Yeah, some serious. Sort of this way. When you start being. Where water. Yeah.
Oh, yeah. Yeah.
Yeah. So it's like, it's little off here. Those are the same, those are a little. Then obviously you get worse and you go over down case. Yeah. And I think like, now we kind of have a problem.
Yeah, I guess that is.
Yeah. Oh, yeah.
It's like. It's been like stuff.
Oh, yeah. Well, it gets like, fraction, you know, you get the difference. You get the shallow water. I think that's next to it. At least, yeah, when you solve for. Yeah. I'm looking at it, and I'll start looking at it. Can you have a for which like the is the 2 points Is the same as. More abstract. Yeah. Because like if you want to think about your version is a non-exceptional approximation to a given dimensional problem. Sorry, so if you want to think about your version as a finite dimensional approximation to a problem, you might hear about like a first correct velocity model. It's like sometimes, I don't know, these sort of convergence things show up in real life in very personal ways. Like, you know about the cookie, right? It's a distribution.
Why does
It don't have. If you try and convert it, you get a
one over one?
yeah, it might be so. But it's, I think it's 1/1%. So essentially, when you multiply it by x, it's asymptotic for x. So you can't take an average of it, but it is a probability. And so if you try and expand distribution and try to take the averages, it actually doesn't. If you take like an of so you have to like track something.
Yes.
The error.
But I think this we
Like it, you distribution of
I hope in the future.
I was thinking, you know, that the first one, I really have to speak with the color, putting this on your research in charity. So I was thinking we could do another for doing, them together to match the color and talk about the project and the goals, and see if we can start with all the research part of it. And then it's more, and I'll try to make it more enrich to, try to put it down and see if it is a, little bit of working on. I think it's perfect because we also manage to balance your whole life. And so if it's too polished or it just everything that you want to I think it actually, I think that was great. And
yeah. Right now, I'm just trying to have different ways that people want to do that you For. I feel like it's better to have something that I can iterate on. Stack it, I want to see nothing stack like you have to really know. I don't know. Yeah.
Yeah, we are because of that.
For the label, if it works. Yeah.
Yeah, but they're bring to put that.
Open your Docker.
So the armband is working now?
Yes, it's working. Very sure. That is very good.
And Frontera is also working.
Yes, it's also working.
Yeah, this is not the
It's 1 year ago.
right. Just no, just do
There's also one thing I want to ask. So yesterday, Poma updated the Jupyter notebook so that it should originally we plan to have all the Frontera command line in the Jupyter notebook too. So that the docker doesn't show up. That's updated.
Yes, like
That's why today we have this mess of we have to like okay. We in the
Oh yeah.
GitHub.
one of the merge probably deleted those instructions.
So some merge.
Yeah.
So Poma commit deleted the instructions
No.
in the Docker.
No,
Poma created it, but something removed it.
some merge.
Some merge
removed it.
removed it.
Don't know why.
Yeah, it should be like this. That that will like help
It
everyone.
should be in the latest.
Yes.
Right now.
Is it? Is it in the latest? You can check that.
Yes.
Yeah, just check the latest one if it's in there. Because if it's in, then I don't have to complain. Maybe just ask everyone to update.
Yeah.
Ah.
That is
I don't know.
original. But anyway, yeah.
Sorry.
It's okay. It's our first time using HPC for.
No, it's actually not.
Not? Okay. It's my first time.
No.
Frontera was the first time. Yeah. So normally we did it in Stuttgart. First time on Frontera, and it's the first time we do it out of the notebook actually.
Yeah, because within the notebook we cannot use the MPI
Mm.
process.
Well, the thing is, previously the container runs fine
Yes.
inside notebooks
Yes.
because the MPI doesn't run distributed.
Yeah.
This new one can run distributedly, then it doesn't run distributed.
I see. So there must be you really have to choose one.
Yeah. So we can just have different versions of it for different workshops that actually suits the purpose.
Yes.
So running on Frontera, we definitely need this one that actually can run distributed. So
Yes.
then if we just have like an old or a single node setup, then the old one is fast.
I see. But the old ones still have the problem of the PY vistas that we can only display in the VNC system. If I use the command line in the job Jupyter, it still cannot run the PY vista. That's why we choose the VNC server. I don't know why it cannot be shown. I don't know whether it's related to the VNC server or not.
Yeah, I think it's probably something in the Frontera setup. But I don't know. I'm not expert.
Yeah.
Yeah.
The display.
Yeah.
I wonder if it's maybe a little bit over ambitious with the setup. Don't know what the others did. I mean, it's very complicated to say.
Yeah.
Yeah, we can wait here.
Yeah, okay, makes sense. Yeah, Camilo was working project. I mean, no, but experience that I applied to, so it's not trigger in the UC version. Yeah, I mean, I'm moving out, but. Camilo also worked, he worked more in the civil engineer side of Oh, we got to mention that. Amazing. I love you.
Yeah. I carried I got all my stuff for this trip. I put everything in this. You know what? I do have a poster. Yeah. Yeah. No. Maybe this one. Yeah.
Yeah, check if the current version still has your things.
Yes.
It's just a little bit sad because everyone put so much effort in it.
Oh, it's okay.
Yes.
I always have trouble.
We are just, you are
Oh,
still
sorry.
showing your screen in case you don't want to show anything.
Yes, I want to stop. Why is my? Where is it? I don't even.
You're sharing on Zoom.
Oh yeah. Okay. Sorry.
You also have your mic on.
Yeah. Can you say something? Can you say something?
Yeah.
No, from your computer, can you say something?
Oh,
Yes, they hear me now.
yes, it's yours.
Hello. Hello.
Yeah. Like say that they, of course they can from like I guess that hard like it's very clear. Like if you
This
like,
speaker?
yeah.
That's a
To me, that seems like there are some situations
yes, that is.
Hello. Probably they hear me.
People attendees, if you can hear me, please say something in the chat.
Yeah, I can hear you here.
Okay.
Hear you here.
Okay. Can someone?
Whoever's on Zoom, okay, post in the chat if you cannot hear us.
Ridwan or Mustafa, can you say something? We are testing.
Yeah, I can hear you. Can you hear me? No?
As long as you turn it on, everything, speakers are saying it will be both.
Can you ask Mr. to say something?
Hi, can you hear me? It's okay?
Yes, you perfect, perfect.
Yeah, that's great.
Here.
Thank you.
Definition. It looks like everyone's doing this. I forget the US just doesn't but it's not
Masaru, can you hear us? Masaru, can you hear me?
But I do feel like I have offended people by putting
Ridwan, can you hear me?
how much like time.
Can someone hear me?
Yeah, I can hear you online. Yep.
That's what they miss, like that institution crash course. Just like trying to be like if you went to the and I lost like to me that should I mean, really it starts with like the money, right? So that's really important. I like to be like, if you're collecting your own data,
We can make a simple test. So,
I don't know.
for instance, can we hear me now? And can we hear me?
I don't know.
Is anyone there hearing me? Masaru, are you there?
It's the chat.
Hey, I'm here. I can hear your voice now.
Yeah,
Clearly.
we can hear you online.
We are just making a test.
Maybe.
Yeah. Can you hear me, Masaru?
Yeah. I can hear you. Probably it's a little bit weak.
Okay, it's weak. How about now?
It's okay. With this
It's okay.
distance, yeah, it's okay.
I should be close to this. Yeah. Okay. Masaru, how is it now?
It's okay.
Yeah, I can hear your voice now.
Okay, you can hear me?
Yeah.
Where are
Yeah.
Where's Marie?
Yeah, there's some weird things.
This is actually Marie's account. Just type your name there. I know that. Why?
A whole 1 year I was in SCOPED.
Yeah, maybe.
I have no idea.
The Seattle was also.
Maybe Cardinal.
It's actually for like the 10 ounces too. I didn't get very.
Oh, yeah.
Thank you.
There will be an update shared in the channel once we debug everything. If you could let us know if it still doesn't work, it helps us. Yeah, let us know in the Slack channel.
Okay.
Yeah.
Thank you so much.
We're doing some overnight rebuilds and we make sure that.
Yeah.
Okay.
Now. Yep.
we can start slowly or quickly. Good afternoon, everyone. So the afternoon session will be dedicated to SpecPAM 3D globe and global simulations, okay? Global wave simulations with SpecPAM 3D globe, unlike what Alice and Jeremy talk about in the morning about dynamic rupture simulations, we are going to be focusing on wave propagation, far field wave propagations. And we just described the source as a point source. We use moment tensor solutions. And I will also let you know how you can take the finite fold effects into account. So this session has been prepared together with Oyon Ghosh. Oyon is here, so he's going to help you with the practicals. Masaru Nagaso and Rıdvan Özturan, these three guys prepared all the materials, okay? Masaru and Rıdvan, they are online. So in case we need their help, they will be here available. And so Daniel Peter helped us to make SpecPAM 3D globe containerized. He had to change the structure quite a bit. And Ian, thanks very much for all the help to let us access to Frontera. So, okay, so as I said, we are going to be focusing on 3D wave simulations, and we will make the introduction to full waveform inversion, what Brian talked about yesterday. But we just want to dive a bit into these kernel calculations and the misfit functionals, just to give you an idea how you can control your full waveform inversion algorithm. And after my introduction, we will start a practical session. You will all log into Frontera, and you will run a forward and edge joint simulation on Frontera using SpecPAM 3D globe, but using a one chunk simulation. I will explain you what one chunk is, etc. I have a lot of slides. I didn't remove them. Most likely I'm going to skip some of them, maybe most of them, to have enough time for the practicals, but I wanted to keep the slides as it is, just to give you an idea. When you later on, if you would like to go through the slides, you can follow them much better. So anyway, so Alice said, unfortunately she left. Alice said forward problem has been solved in seismology. Actually, it depends on your problem and scale. But the forward problem, when it comes to global seismology, traditionally is Okay, can you hear me, online participants now? Okay, perfect. We may need to change.
Julian, Akash, can you do sound check?
Masar or Rıdvan?
I can hear you guys.
Okay.
Yeah, no sound.
Okay,
So,
can you hear me now?
Yes.
Okay, perfect. Apologies for the technical issues. Okay, let's. Okay, so as I said, we are going to be using SpecPAM 3D Globe, which is not so much different than what Brian yesterday talked about SpecPAM 3D packages. Actually, I just wanted to highlight this specpam3d.org website where you can find all these SpecPAM 2D, 3D packages, and the site, and together with all the additional software for full waveform inversion, and the web page is specifically dedicated to Dimitri Komatic, who is the main author of the SpecPAM packages. So, as I said, it's SpecPAM 3D Globe is not so much different than SpecPAM 3D Cartesian, what Brian talked about yesterday. Of course, there are differences, but in the end, we are just solving the wave equation, okay? And the main difference is that, as you may understand, SpecPAM 3D Cartesian uses Cartesian coordinate system, and SpecPAM 3D Globe uses spherical coordinates. So that's one of the main differences, which allows us to address the physics of the medium much better, which I'm going to talk about later on. So here, as I said, all these packages, what they do is they are solving the equation of motion. So here you have the equation of motion where S denotes displacement, where you have the density times acceleration, and you have the divergence of the stress tensor. And here we have a seismic source denoted by F. And in our problem, the source is an earthquake, which is described by a moment tensor at a specific location multiplied by a source time function, okay? And if we use the linear relationship between the stress and the strain tensors through the fourth order elastic tensor, and if we impose the boundary conditions, at the global scale, we have just one boundary condition, which is the free surface, where the tractions go to zero. So that's probably the only advantage of the global simulations in terms of numerical issues. But what we are going to do today, we won't use the full globe. We will just simulate wave propagation in one chunk. The globe consists of 6 chunks in the global version. So we are going to be using one chunk just to make the simulations more feasible for today's practical session. And in that case, we will need to use some additional boundary conditions, of course. We will have absorbing boundaries on the sides of the chart, okay? And the initial conditions are set such that the displacement and the velocity is 0 at time t0, okay? And then you can solve the equation of motion using a strong form, using a strong method such as finite difference, which is commonly used. It's still pretty popular because of its ease of implementation. And for a simple medium, actually finite difference can beat all the other numerical methods. But in our case, in the SpecPAM 3D globe, in the spectral element, we are using the spectral element method, which is the result of the weak formulation of the wave equation, which is just the integral form. As you see, instead of trying to solve the differential equations, we are just trying to solve the integral form of the equation of motion. So what is the advantage? Specifically, why we are using spectral element method. We need to use spectral element method for multiple reasons, especially for global scale simulations. The first one is that spectral element method combines the advantages of the flexibility of the finite elements when it comes to meshing complex structure. It has quite some advantages, and the accuracy of pseudo-spectral methods, such that because of the basis functions and the formulation of the problem. But the main advantage for the global scale simulations is that what we call the mass matrix, when you try to solve the equation of motion, there's a mass matrix that you need to take the inverse of it because of the chosen basis functions in the spectral element method, which are the Gauss-Lobato-Legendre polynomials. They have some nice properties and they make these mass matrix diagonal. And it's much easier to take its inverse. And this is how the spectral element method has made the global wave simulations feasible. And that's the main reason why we are using this. And here is a nice movie from David Peter. So the coffee cup simulation. So assume that you drop your sugar into your coffee cup, and then let's initiate it again. And then you see, you generate seismic waves, not seismic waves, acoustic waves propagating. And in the coffee, where the acoustic wave simulations are coupled with the elastic wave simulations when the waves start propagating in the ceramic part, right? So this is a good illustration of the acoustic elastic wave coupling in the spectral code. From geophysical point of view, if you can solve this problem, if you can solve this coffee cup problem, that means you can also solve the wave propagation inside the Earth. Why? Because we have the fluid outer core, right, surrounding the solid inner core, and where we need to couple the wave simulations in the fluid outer core with the elastic simulations in the mantle and in the inner core. And if you solve the coffee cup, you can also run wave simulations of the Earth. And yes, these are the features that or the parameters that you can all take into account in your global simulations with the SPECFAN 3D globe. You can, we always say acoustic elastic, but actually our problem at the global scale, even at the regional and continental scales, is unelastic. So you can take attenuation into account, you can take the ellipticity of the planet and the rotation of the planet into account. The self-gravity can be implemented. You can directly implement the topographic bathymetric variations. Right now in the SPECFAN 3D globe, we are not running wave simulations in the ocean layer because it's computationally super expensive. Instead, we are taking the ocean load into account. You can have anisotropic simulations, and you can compute adjoint kernels for the full waveform inversion. This is what we are going to do today. The code can be run both on CPU and GPU computers. And it's not limited to Earth. Now Mars and Moon are also implemented. You can run simulations for Mars and Moon. And I heard that Brian is interested in implementing the Venus. So you can implement your own planet into SPECFAN as well. So this is something that I really like. GPU-CPU comparison of the spectral element method. So actually, on the right-hand side, the CPU is also running. It doesn't mean that it's not running. So it's just too slow. Okay. So actually, if you have access to GPUs, then you can drastically speed up your simulations. But of course, there are all these discussions that what I'm telling you is valid if you have the same number of CPU and GPU cores. But of course, GPUs are more expensive. So there's always this discussion that, yeah, but they are more expensive. We don't have access always the same amount of GPUs. That's true, but there are supercomputers such as Oak Ridge National Labs, former Titan Summit Systems, and the current exascale computers Frontier. There are GPU supercomputers where you can have access to thousands of graphics cards, which can dramatically speed up all the simulations. Well, in terms of the human time. Okay. So one of the most important aspects is the meshing part of the problem. Alice already talked about this. I will just tell you what the mesh is in the global version. First of all, we are not changing the mesh all the time in the global version because of the longer wavelengths we are interested in. So the default mesh or the current mesh we are using is the PRAM, designed for the PRAM mesh, which takes which honors the first order discontinuities in the PRAM model, like the MOHO upper mantle discontinuities, core mantle boundary, inner core boundary, etc. Okay, and to speed up the simulations, since the wave velocity increases as you go deeper, then basically automatically your wavelengths increase. So that's why you don't need the same sampling, the spatial sampling in the deeper part of the Earth to be able to achieve the same resolution for the same wavelengths, right? So that's why at certain depths, there are mesh doublings. This is to speed up the simulations. However, the problem, there is still a problem coming from the crust. You know, 90% of the problems in global seismology is coming from crust, and it's the same in numerical simulations because crust is the slowest layer, which makes the simulations expensive. So ideally, to be able to capture the crustal effects, we need much denser mesh. The problem is a bit tricky on Earth because there's a dramatic difference in the crustal thickness variations from oceanic crust to continental crust, right? Oceanic crust is about 7 kilometers, the blue regions, and you can have up to 70 kilometer crustal thickness underneath continents, such as underneath Himalayas, Andes, and you have a cross section from Pacific Ocean to South America, crossing the Andes, and to achieve a good resolution, what is done in SPECPAN is that the crustal thickness in the oceanic crust, mainly, if the crustal thickness is less than 15 kilometers or larger than 35 kilometers, the mesh honors the MOHO. Okay, so underneath the oceanic crust, we represent the oceanic crust with one spectral element, and then we use 2 or more spectral elements to sample the thicker continental crust. And if the crustal thickness is in between 15 and 35 kilometers, MOHO is not honored. Strictly, the mesh just runs through GLL like this. Why do we need it? To be able to sample the thin oceanic crust much better, to be able to have more sampling points in the oceanic crust. There are other methods to try to speed up the simulations, but this was what we decided years ago, and still we use this mesh for our simulations. And as I said, you can also implement any planet, any model. So this is the mesh we designed for one of the reference Mars models. It was SOL and SPON at that time, which is outdated. Now we need to update, but we can still use the mesh designed for SOL and SPON model, similar to what we do for Earth. And this is just to show the effect of the crust. So this is a simulation on Mars. So the background model is radially symmetric. We just superimpose the crustal thickness variations and the topography. And on Mars, we have a distinct dichotomy between the northern and southern hemispheres, both in topography and the crustal thickness variations. So if you look at the simulations again, okay. So if you have just a radially symmetric Earth model, then you should have all these spherical wavefronts, right? However, this region, this is the largest crater on Mars, Hellas Planitia. You can see that this is where the crustal thickness gets thinner. So that's why when the surface waves propagate through this region, you can see how they speed up. Okay. So crust can really have a strong influence on surface waves, which is a super crucial subject. And you first need to make sure that your model, your crust, they're all properly implemented, and you can take care of the complexity properly before anything. So if you have all these stations distributed everywhere, we are now back to Earth, not on Mars. And if you record these wave fields at different stations, you can get such a cross-section. This is an example for an event in Argentina at a depth of 571 kilometers. So the seismograms are filtered from 17 to 60 seconds, okay? So you see the seismograms plotted as a function of eccentric distance. You can see the station codes on the right. The black ones are the observed seismograms, the field seismograms, and the red ones are the results of SPECT and 3D globe simulations for the model S362 and crust 2.0 of the crust. So what you see is that basically, yeah.
Do you like the moment tensor solution for this event? You assume a solution and you compute, okay.
We typically get the moment tensor solutions. If you are working with the global events, we typically get the CMT solutions from global CMT catalog. Okay. But you can use any moment tensor solution, okay? And so in this case, the moment tensor solution came from global CMT.
Okay.
And you can see that the seismograms are aligned on the P waves. So you can see that there is quite some good agreement on the P waves. And this is one of the smoothest global models. Now we have much rougher, much more detailed global models. But S362 together with crust 2.0 for this earthquake did a great job in explaining body waves. Whereas when you are in the surface wave regime, you can see the discrepancy. And it's not a problem. Actually, this is when our job starts as tomographers, right? Because now our goal is to try to minimize this difference between the observed and synthetics through an optimization technique to find the best model that would minimize the misfit between the observed and synthetic data. So that brings us to full waveform inversion part, right? I would like to say a few sentences. Why do we want to use 3D wave simulations in seismic tomography? Because it's computationally expensive. If you would like to perform full waveform inversion at the global scale, you need world's fastest supercomputers. It's not something that you can do on your laptops or on a modest cluster. For instance, we have used, at Princeton Group still uses Oak Ridge National Labs supercomputers, and which are, at the time, for instance, when I started using, Titan was the #1 supercomputer, and now Frontier is #1. And currently, my group is using UT Austin's Frontera system. So you really need a large supercomputer. So why do we want to do this? Do we have too much time, or do we really need it? So first of all, we are now at a regime where details matter, in my opinion. We need to, if we would like to further improve the resolution of the current tomography images, we need to take the full complexity of wave propagation into account, okay? Because ray theory is a high frequency approximation, and it has been already well documented that now we are in a regime where we need to take the finite frequency effects into account. What are finite frequency effects? So basically, what is the consequence of finite frequency effects? So this is a nice figure from the classical banana donut paper showing the sensitivity of a P wave to Earth structure. So normally, what ray theory tells us is that assume that you have a source here and a station there. And the ray theory, if you are running your wave simulations in a radially symmetric Earth model, ray theory tells you that the waves should follow the ray paths, right? Which goes to inside the middle part of this banana, right? However, finite frequency theory tells you that, paradoxically, the sensitivity of your wave to wave structure along the ray path is 0. All the yellow part is 0. but your wave is sensitive to this zone denoted by red color, which is the Fresnel zone. And this is where the banana donuts are coming from. So what is the consequence? If you keep using ray theory to further improve the resolution, and especially if you are working with long periods, or if the wavelength of your waves is larger than the scale length of your heterogeneities, then you have this problem, because ray theory breaks down for such a case, okay? So that means if you want to use ray theory for this problem for the same periods, right? That means you are going to update the wrong parts of the model. That's going to be the error you are going to introduce to your model. So that's why I say we are at a stage where we need to avoid approximations and corrections as much as possible. There are other things as well, but I would like to keep it short. So today, your practical will be about to compute a banana donut curve. So how can we calculate a clean banana donut? So the thing is that this figure is from the classical banana donut theory, which was computed analytically. Now we can compute it numerically, and this is what you are going to do. And actually, the main difference between the analytic and the numerical solutions will be that we only have, remember, we only have the analytic solution for radially symmetric Earth models. But now if you can compute these sensitivities for 3D background models, then you can iteratively update your models, or you can perform full waveform inversion. So this is where the numerical methods come into play, okay? And a question for you, should we have clean kernels in full waveform inversion? I can give you a spoiler. Yeah.
No.
No, that's the right answer, but you know why?
Because you already have the information, the prior information about the subsurface, so the ray path will actually already be affected by the structure.
Yes, and in addition, if you would like to, and that's why you are going to do this assignment, if you want to have a clean banana donut, this is a requirement for ray theory actually. Because in ray theory, you have to isolate every phase of interest because you need to reproduce them, right? That's a requirement for that. But in full waveform inversion, we basically, let's go back to the seismograms. Basically, we can model every wiggle numerically in our seismograms. So that's why we don't care which portion of the seismograms we are using. So you can use anything and everything in your data. Body waves, scattered waves, surface waves, whatever you can select, okay? So that's why if you select everything, of course, every portion of these waveforms will be sensitive to a different structure. And eventually, you may not have clean banana donuts. You will only have clean banana donuts if you compute them for a radially symmetric Earth model, for a specific well-isolated phase, etc. And you are going to demonstrate this because whoever is interested in doing full waveform inversion, I still find this exercise pretty useful because it's not that easy, trust me. Okay, and most of my students spent a couple of weeks to try to, and Carl also made the same point. They spent a couple of weeks, although they know everything, just to get a clean banana donut from numerical simulations may not be that straightforward, okay? And this is what you are going to do. So what is this? Let me also say a few things about the optimization part. So basically, what are these kernels? What do they tell you? Basically, we are computing nothing else but the gradient of a misfit function, okay? So if you can calculate also the second derivative of your misfit function with respect to model parameters, which is called Hessian, then you can update your models through a Gauss-Newton method, which is good. But in these numerical simulations, we don't have access to Hessian because it's computationally infeasible. Okay, so we can only compute the gradient. If you have the gradient, then you can use a gradient-based optimization technique to update your models, such as steepest descent conjugate gradient, BFGS, or LBFGS. Okay? I just skipped this. Let's come to the kernel part. What you are going to be doing in your assignment or practical. So, assume that you have a misfit function, a waveform misfit. This is what Brian yesterday showed us. So this is the difference between synthetic and observed data. You should just be careful with your convention because you can also write it observed minus synthetic. Whatever you do, just make sure you define your convention, okay? And then you compute the gradient of this misfit function. This is the difference between synthetic and observed times the perturbations in synthetics, okay? Which gives you the gradient. So now if I write these perturbations in synthetic wave field in terms of Born approximation, so I can rewrite my gradient as the misfit between the synthetic and observed part, and the rest is the Green's function. Born approximation, where we have the perturbations in density times the Green's function and times the acceleration, and then plus the perturbations in elastic tensor. And you can also add now the unelastic parameters, etc. here, okay? So if you use the reciprocity and reverse everything in time, you can define a new wave field using this Green's function and the misfit between the synthetic and observed data, right? Then this would be a new wave field, which we will call adjoint wave field. So here is the Green's function. So the Green's function is the same Green's function you use for your forward simulations. Now multiplied by a source term, which is nothing else but the misfit function. The misfit between your synthetic and observed data. And now I'm going to call that term adjoint source, okay? This is what you are going to compute for a chosen misfit function. And to be able to compute the banana donut kernels, you need to use travel time, cross-correlation travel time misfit, okay? So this is what Brian already showed yesterday, the construction of the adjoint kernels, sensitivity kernels, pressure kernels, or eventually nothing else but the gradient of your misfit function. So basically it's based on the interaction of the regular and adjoint wave fields. So the only difference between the regular and adjoint wave field is the source term, because the Green's functions are the same. In one case, you are using a regular earthquake source. In the adjoint wave field, you are just using an adjoint source based on the misfit function. That's the only difference. And now, if I write my gradient in terms of model parameters, here it's the perturbations in density plus the perturbations in your elastic parameters. So just look at the density kernel, how it's computed. Basically, this is the density as a function of space, which is the result of the multiplication of the adjoint displacement wave field with the forward acceleration. So indeed, that tells you that you need two simulations, one for forward, one for adjoint, and then you are good to go to compute the gradient of your parameters, okay? And this is what you would get as banana donut kernels if you make careful measurements. Here you see the banana donuts for a P wave, where the seismograms are filtered at within different period bands from 9 to 27 seconds. I don't know if you can read, but can you guess which one is for the 9-second P waves, which one is for 27 seconds P waves? No, Cash, I'm not asking you. Yeah, see.
So the 9-second one should be the fatter kernel. And then, no, it's the opposite.
Yes, it's the opposite. because ray theory is an infinite frequency theory, right? So the shorter the period, the narrower the banana donuts. So this is for 9 seconds, this is for 27 seconds. So that means if I decrease the period range in the limit, the banana donut will collapse onto a ray path. Then you will have the ray theory. Okay? And you can now compute these banana donuts for any phase you like. Here you see the banana donuts for SCS phase, the core reflections, or outer core, inner core phases, surface waves, or even you can calculate some exotic phases, such as the SS precursors, which are sensitive to upper mantle discontinuities. And then you can see how the kernels can be complicated. They are no longer clean banana donuts. And these are still computed in 1D background models. And then you can construct any model. Once you have these kernels, all you need to do is to make these measurements and calculate these kernels for every source receiver pairs, for every time window, and then simply sum them up. So basically, you can compute these kernels for multiple stations because the simulations cost, the simulation cost is independent from number of simulations, but depend on the number of earthquakes you have, okay? So you can compute, if you feed in the adjoint sources of all the measurements for one earthquake, you can immediately get the gradient for one event, which is called event kernel. And then to get the total gradient, all you need to do is just to sum up all these event kernels from different earthquakes. It's just a simple summation. And this is what you are looking at is from the GLAD N25, which is one of the global models that was computed using this adjoint tomography, and showing the negative wave speed perturbations, which are nothing else but the mantle plumes. Okay. One thing I would like to highlight, you can use any misfit you like. You are not tied to waveform misfit. Today we are going to use travel time misfit, but you can define amplitude misfits, instantaneous phase, envelopes, etc. You are free to design whatever you like. But then you will get what you deserve. Okay, yeah.
What is the instantaneous
Say it again. I can tell you. It's just rather than looking at the cross-correlation travel times, you can compute the instantaneous phase, which is the Hilbert transform, a Hilbert phase. Okay, so the phase not as a function of frequency, but as a function of time. You define the phase in Hilbert domain. Okay, it has some advantages which I like. Yeah.
Can I use L1 for the misfit?
You can, but then you need to update your adjoint source accordingly. That's the trick. You can use any misfit you like, but provided that you will update your adjoint source accordingly, because the adjoint sources change. Okay, so here you see, for instance, a P-wave kernel for different misfit functions. So you see the seismograms on the top and observed as synthetic, but they are both synthetics. And then this is the adjoint source for instantaneous phase. This is for the envelope. This is for travel time, which you are going to use, amplitude and waveforms. And then you can see how the sensitivities change depending on the misfit you choose. So the Earth is the same, the model is the same, but the sensitivity is changing. The way your waves see the Earth structure changes. So ideally, you should be able to get the same result out of whichever misfit function you use, but you need to choose it carefully to control the speed of convergence, or if you would like to increase the resolution, or if you want to have a robust measurements. So every misfit function has advantages and disadvantages. You need to choose it carefully according to your problem. Okay, just as an example, this is the waveform misfit, and I like to use the normalized version of the waveform misfit. especially when I combine different measurement windows. And this is the adjoint source, right, for the waveform misfit. And today you are going to use the travel time misfit, cross-correlation travel times.
Sorry, this normalization is because of the magnitude of the
to balance the magnitude and to be able to balance different amplitude phases. So if you don't add this normalization and if you don't use waveform misfit with windows on a window of data, then always the largest amplitude portion of the seismograms will dominate. In our case, the surface waves.
Okay.
If you want to give the same importance to body waves and surface waves, different amplitude phases, then we like to normalize every measurement window with its own energy. Then they are kind of balanced. Then in your gradient, you can still have the body wave and surface wave sensitivities together. Okay. And it also balances the magnitude differences between different earthquakes. So in the cross-correlation travel time, you are looking at the time difference, arrival time difference of the observed and synthetic data here, right? It's again L2 norm. And if you calculate its gradient, this is your misfit times the perturbations in travel times. But we need to derive it in the way that we write it in terms of perturbations in displacement. Remember the waveform misfit. So if you rewrite it in this form, you can look at Datland's papers. I will not derive it right now. So you see that the gradient, this part, is nothing else but the velocity of velocity seismograms multiplied by a measurement window. This omega is the time window, and multiplied by the perturbations in displacement. And then normalized by a number which is given like this, which is just as constant, right? It's integrated over time. It's the multiplication of displacement with the acceleration. It's a weighting term. So that means your adjoint source is nothing else but the velocity seismograms. And then all the other factors will control the magnitude of the kernels or the gradient. So that's why when you write this in this form, this is the in this form. That means your adjoint source will be this part. You just exclude these perturbations, and this is your misfit. And this is your misfit times this gives you the adjoint source. So basically, in the banana donuts, that means this is going to be a constant. You can also exclude measurements for a while. If you want to compute the banana donut kernels that I showed you, it's okay just to calculate this portion. Then what you do at the end is to multiply by your misfit, travel time misfit. Okay? So what you should be careful, or to test yourself if you are doing the right thing. Assume that your observed, the structure, your observed seismograms, let's say, are faster than the synthetics, which means observed seismograms will arrive later, or the synthetics will arrive before, right? And then that means, according to this convention, just be careful when we take the gradient, there's a minus sign here coming from the derivative, right? So that means your misfit will be less than 0, negative, right? So there will be a negative, there will be another minus sign here, then the rest will be all positive. If your observed seismograms are slower, then they will, sorry, I should have, there's a typo, this should be greater than the synthetic arrival time, then your misfit will be positive. This will be positive, but you still have this minus sign here. Yes, you have a question.
I'm just repeating to myself.
Okay.
It's okay.
So basically, by looking at this, you can understand what kind of kernel you are going to get. And when you are calculating your own kernels, we can discuss this again. I will repeat how you can check, verify if you calculated correctly. Okay. I think I will stop here, or maybe I will just say a few things. I wanted to talk about the inelastic kernels, but maybe later on the way when you are running simulations, we can come back to inelastic kernels. So this is going to be your problem. This is Oyoni is going to guide you through. You are going to run forward and adjoint simulations for January 1st, 2024, Japan earthquake, which is magnitude 7.5. And you will use two stations. One of them is Tara, is basically your wave field will sample mainly the oceanic crust, and the other one will be mainly continental crust. So pay attention to your synthetic seismograms. You are going to compute first the synthetic seismograms for these two stations using a global model S4TRKS together with a global crustal model, crust 2.0. This is your computational domain, okay? And then you can make some comparisons to 1D synthetics, but we won't ask you to compute the 1D synthetics. You can just download them from Shake Movie website, and actually we provide them to you. And that was the question. We are using moment tensor solutions. So what is the moment tensor solution? There is one thing that I would like to clarify. So you can get the moment tensor solutions in this format from Global CMT catalog. So the first line is the solution for the preliminary solution of the source parameters, which is called preliminary determination of epicenter. So where you can see that it's the year, month, day, hour, minute. This is the origin time of the event. Latitude, longitude, depth, body weight, surface weight, magnitude, and then there is the event date. So if you compare the first line to this part, the parameters are different because the first one is related to the source parameters at the nucleation point of the rupture. But SPECPAM uses centroid moment solutions, centroid time, and centroid locations, which is not necessarily the first rupture time, which is typically when the most of the moment is released along the rupture. Okay, so that's why you will see differences in the latitude, longitudes, and the origin times. Basically, you can get the CMT time by adding this time shift to the PDE time. So that time shift is the difference between the CMT and the PDE times, okay? And then you have these 6-component moment tensor components, moment tensor here, okay? And this is how you can calculate the scalar moment from that. And SPECPAM always uses CMT parameters, CMT time. And one thing you must be careful, the zero time in SPECPAM synthetics always correspond to CMT origin time, okay? And then we use a Gaussian. Typically, it's good for the periods we are working with. We assume that our source time functions are Gaussian. So where we convolve the synthetics with a Gaussian source time function with a half duration, the half width of the Gaussian equals the half duration of the rupture, okay? And the sector corresponds to the CMT time. So that's why if you look at SPECPAM synthetics, they start from negative times, just because of this. Because everything is arranged such that the zero time in the synthetics will correspond to event origin time, which is the CMT time, okay? But you can also run finite fault simulations, because we know that especially for a magnitude 7.5 event, finite fault effects can be important. And this is the solution from USGS for this event. And you can also run simulations like this. This is a figure from Rudwan. Basically, all you need to do is to add multiple moment tensor solutions in one file. Okay? And that's such that this is the first time, the first moment tensor pixel, and then with certain time intervals, the other moment tensors are initiated.
How the total moment of the solution, the first solution, is distributed like the the finite fold? I mean, how
I don't have much information about how USGS constructed
Okay.
this finite fault model. It's
Yeah.
something that we just.
we use?
In
Okay.
the way of the USGS, you have a moment, seismic moment distribution with time, and you produce.
And here you see the comparison how the synthetics differ from point source to finite fault model compared to observed data. Okay. And here are some good reminders for what you should be careful about when you are comparing observed and synthetic seismograms, and Oyon is going to go through them anyway, so that's why I'll skip. I strongly recommend you to look at Shape Movie website of Princeton, where you can download 1D and 3D synthetics for a specific Earth model, of course, for every global CMT earthquake. So whenever an earthquake happens somewhere on the Earth, larger than magnitude 5 or 5.5, global CMT system just triggers the Shape Movie simulations, and then the synthetics are computed for all the global networks, and then they are stored on the servers. So you can go to this website and then download 3D and 1D synthetics for any earthquakes. But of course, you can run these simulations yourself, and this is what you are going to do today, and with the availability of changing the velocity models, etc. Okay? We can discuss how to compute a clean banana donut on the way. Now, Oyon is going to take over to guide you through the simulations. Yeah. Yeah. We had to change the computer, so Oyon is logging on Zoom right now.
I cannot share my screen.
Yes, you can.
So if everyone has gone, like, look at the link for the GitHub repo, which we posted in the Slack. Yeah.
Oh, maybe.
Yeah.
So now everybody will need to log in Frontera. You will run everything on Frontera, all the Jupyter notebooks, visualization, everything will be on Frontera. Are you using VS?
My favorite girl. Huawei. Yeah.
Yeah, just.
Yeah, I saw. We said that would create the standards. That's not that. Is it like? It's, yeah, it's just, so Newton's method is when you have the hash you use that, you're trying to create stuff, because you know it's like second order information. Okay. Then VFGS is when you guess it what the hash is. Oh, it's in previous iterations. And OVFGS is kind of a trick. You can use a limited amount of memory. Instead of storing a whole matrix, you just store.
So,
Yeah. Yeah. Oh, that sounds cool. Yeah.
so everyone can try logging into Frontera with the SSH command. I think you don't need to use the -y. Just use SSH your username at Frontera. I think you have done it in the morning.
I'm still down.
Yeah. So
Is this one? We can take my, I want to take a board. Take my board, go on for it. It will work. Then just take this card.
Just calm down. You're fine. Yeah.
Siempre no por el medio. En Misfit, en el fondo, la forma que tú uses para cuantificar las diferencias de los programas te muestra distintas cosas de la estructura que se está moviendo en la otra. Se queda por ahí. Exacto.
now, I think if you're into Frontera, you can go to the Scratch directory.
Está ligado por lo que entendí. Finalmente sirve para
Just go to Scratch directory
actually
on Frontera.
to Misfit. Realmente va a estar
You should just type cd$scratch.
Yeah.
Everything is working so far.
Copy and even clone the repo there.
Yeah, that's I just got the Well, so I'm still running, but that stops me from.
What do you
It's the last year. Oh, I opened it in.
So if you now, after cloning, if you now look at the directory, there you will find our SeisSol directory. You should go inside there.
Just go inside the workshop directory once you clone the notebook.
Yeah.
That's pretty.
And you also have the command in the GitHub repo how to run a Jupyter notebook. So you don't need to create the binary files for the 3D globe here. They're already compiled and put in a container. So you will use that image. So you don't need to build your spec frame right now. So you just need to run the notebook.
So the Jupyter notebook is running on our local laptop?
No, the Jupyter notebook is running in the Frontera. So
you should clone.
I did. I got the link, but
Did you log into Frontera?
Yeah, no, I did everything on Frontera, and then it gives me the HTTPS, and I just pasted it.
Yeah, you can open the browser in your local.
That's what I'm saying. Yeah.
You basically in
It's a
the
little
browser, but you open
counterintuitive,
it.
yeah.
It's quite different from SeisSol.
Yes.
Yeah.
Also.
You want to aspect.
I think maybe Monster just like this.
Okay, now copy this line.
But you're still right. I mean, what's the share? I don't know, I'm just like. It's been, yeah, I've been running for like.
Yeah, I think.
But
So now you need to submit a job.
So you can test the status of your job using this command. Skill user. So it's still not running yet. Like you can see the status of the job is pending. I think whenever it will start, you can open the Jupyter notebook after that.
Okay.
Do you want us to pause that once we have the notebook, Jupyter notebook open?
Sorry?
Do you want to stay on of this question? Where do you want everyone?
No, you are submitting a job. Now, submit a job.
I already did all that.
Okay.
Yeah.
So that's
This is, I'm down here.
Okay.
Okay.
How long is for?
Like 10 minutes.
Oh,
No, you can keep it like this. Yeah.
So how many of you have your job running? Got your job? So you can use it.
Can everybody run a job on Frontera? Are you all at this stage, or is there anyone who hasn't?
If you use the tail Jupyter.out, you can see the link where you can, if you copy paste the link, you can run the notebook from there.
Excuse me? We cannot wait for the job notification. No, just submit the job and stay there. We will use, I mean, now you are resolving a note to work on, okay?
Some people is getting a message that.
Now, everybody will be running simulations on a single node on Frontera. So this is what you are reserving right now.
Yeah, I know. Okay, and I think you need to run the first notebook on your phone.
The first, is that the process?
Yeah, this one.
So not the one with Docker?
No, so the Docker and the local, there are online folks who can use. Okay, so for the online participants, you can use like the Docker one or the the local machine. But for the in-person here, you only need to run this one, the first notebook.
So anyone in this room, please use the first notebook.
If you're running it on front
The
end.
other notebooks are for the remote participants who will
Yeah.
not be able to run on Frontera.
Because the simulations, like their notebook does not have the simulation part because they cannot run simulations on local machines. So they will only use the provided synthetics to calculate that.
There's an scratch error.
Sorry?
Some error on this machine. That's it.
So So I will stop here a bit so that everyone can open the notebook in their.
Did you do?
So how many are here? After the notebook?
Okay, so you should be scratching and you own the repository.
And that's one. I don't know why.
You can celebrate one.
Maybe transfer.
So you have no problem. So this is
So everybody, please make sure that you submit only one job. Everybody is allowed to submit only one job. But if you try to submit more, you will see another list. So no problem. So basically, now we are running into the first challenge of these large scale simulations, although this is not really large scale. You see that you cannot run these simulations on your laptop. Okay? You need multiple processors. And that's why you need a cluster or a workstation, because this is still small enough to run on a workstation with multiple cores, of course. Okay? So is everybody able to run a job and then initiate the notebook? You haven't? What? Yeah, but most likely already can run the job.
She said. Yeah, that's right.
This is young.
Yeah, probably don't have the permission. Nobody can pay.
Right, now. If you write his username correctly.
Yeah, you can.
This is the trouble thing with the.
Did you reserve or send your username? Yeah.
So should we go forward or there's
Is everybody okay? Anyone who hasn't succeeded to come to this stage?
Okay.
Okay, you can go.
Okay, thank you. So I think the first cell is pretty self-explanatory. You need to run this modules, import these modules, the Python modules which we want to use.
Speak louder.
Yeah. The first cell may take some time to run, just wait.
Just run the first cell and then wait.
You're right.
Yes. So we'll start from scratch. So we'll start with a CMT solution. We'll try to use that CMT solution to download data from the IRIS servers. So the first two cells will help you to do that.
So this CMT solution is also what you are going to use during simulations. But we need to download these kinds of files in advance.
So I have given the link for the Harvard Moment Tensor page where you can see you can download any event you want. You can just go around and check that website, the link I have provided. Yeah, and also the link for the Shake Movie website, which Ebru told earlier, you can download synthetics from there also without running simulations.
But note that our 3D model will be different. So if you cannot match your simulations with the Shake Movie, it's because of the background models will be different. Okay.
So this is just to plot the event on the globe and now this cell will download the observed data. So I think if you can look at those parameters, we are downloading data for two of the stations, Bork and Tara, which we mentioned. One will be in the continent and one which will be in the ocean, and they are at similar kind of epicentral distance. So we are requesting from IRIS.
Like 30 degrees?
No, they are around 50 degrees. Okay. Yeah. So I think this is like OpsPy utility, which is very easy to implement and download data from.
And actually, you are not downloading data. When you run this cell, you already have these seismograms downloaded. So when OpsPy realizes that the seismograms are there, then it doesn't re-download.
So we already provided the downloaded seismograms.
But if the seismograms are missing, then it will start downloading from IRIS.
So these are just introductory shells to plot all of this. So now we are going to main simulation part of our notebook. So there is a directory called the simulation where we will run where our spectrum 3D globe structure is present. So to run a complete simulations, these files, you need to have these files present. Otherwise the code will throw an error. So you need to have the data folder, data directory where you have the CMT solution, the stations, the PAR file. So the CMT solution is the downloaded one, we can use that. And the stations file looks like this. You have the station name, the network, the latitude, longitude, elevation, and also burial. So yeah, you need to give this information in the stations file. And also there is the PAR file. I think that's a pretty important parameter which you need to carefully construct before running any simulation. So we'll look into greater detail on that file.
And by the way, when you download the SpecFam package and go under this data directory, there are other files as well. All the model files from different models, they are stored under data directory. Okay, but today we are using one of the default models, and you will be playing with these CMT solutions, stations, and PAR files. Okay, to set up your simulations.
So, and also you need to have these output files and the database MPI directory. Those they will be empty directory before running your simulations. They will be populated once you run the simulation. So you need to create those directory at first.
So basically, you first need to run the mesher, which will generate the mesh for the chosen velocity model. And then when you run the mesher, all the mesh files will be dumped onto database's MPI directory. So if you go to that directory after you start running, you will see the mesh files up there. Then all the seismograms, etc., and the timestamp files, etc., will be stored under output files. So if you want to see where your seismograms are, you should go and check output files directory. Okay? So that's why those directories must exist. If not, the code will crash.
So now I will briefly go over the parameter file. What are the main important ones? So I have highlighted some of the things. The simulation type, it should be the one. So you can choose different types of simulation. There can be adjoint simulations. There can be for the kernel calculations. You can also use the forward simulation. So as our first step will be to run a forward simulation to get the synthetic set every station. So our simulation type should be one, and the same forward is an important part before you run an adjoint simulation. So to run the adjoint simulation, you need the last frame of the forward simulation. So if you are planning to do a adjoint at kernel calculation, this shape forward should be changed to true. So otherwise the adjoint simulation will fail. It needs the last frame which is calculated from the forward simulations to start. So this part, we'll change this later before submitting our first job. And here you can, this is the number of chunks. You should be careful that as now we are using only one chunk because of we have limitations in the number of nodes we can provide to everyone. So as we are running in, we will be running only one chunk simulation.
So if you want to run a global simulation, you need to set this to 6. Okay, because the globe consists of 6 chunks. But right now it should be 1. Right now, don't play with these parameters, especially these ones, please.
Yeah, because this parameter fixes the chunk region, the region where we want to, and so for our simulations we have fixed this. So don't tamper with this, otherwise you will be running simulation somewhere else, or you can. Yeah.
What is the maximum width for a chunk?
90 degrees. You see this angular width, the first 2 parameters, angular width, psi and eta, 90 degrees.
Okay,
it's a 90 by 90.
Okay.
But you can change it.
Yes.
You can make it smaller.
Smaller, exactly. For a regional
But not
model.
larger. That's the maximum.
Okay. Yeah, and the next parameter is the NEX, xi and eta. So xi, the NEX xi decides the number of spectral elements you need to place, like in the x direction, and the eta is the number of spectral elements in the depth direction. So this parameter directly controls the resolution of your simulation. So we can use 96, or there can be high resolution simulations also, but you need more cores to run them. So we have fixed them to 96. So all the models they have run with 256, like GLAD models are made with 256 the spectral element simulation. So they are much more. So they have much more higher resolution, but here your resolution will not be that good. And the number of n-probe, this controls the speed of your simulation. So we are trying to have 6 processor for like one side, 6 on the other side. So there will be 36 cores which you will be using for our simulation.
Well, just clarification, it's not the radial direction. It's NEX is it shows the number of spectral elements at the surface on each side of each chunk. Okay, so on this side you have 96 elements, on this side you have 96 elements. It's like this, horizontally, okay? So in total, at the surface, you have 96 times 96 spectral elements for one chunk. For the entire globe, times 6. As you go deeper, the number changes. Why? Because we have doublings at certain depths. So you can calculate how many spectral elements you have for your entire dome.
And the dimension of the spectral elements in depth, this is controlled internally by spectrum?
Yeah, because now, as I tried to explain in my presentation, we are using the mesh designed for, pre-designed for trackable.
Okay, so you can play on the horizontal.
Yes, you know, we have a mesh which honors the first order discontinuities. Now you can play with the number of spectral elements to increase the resolution or decrease the resolution. Basically, you just change the number of spectral elements, but the mesh is the same.
Oh, okay.
So, so as we have fixed models for the globe, you can choose. There are various models which you can choose. You can read that parameter file. There are lots of models. So we'll be using S40 RTS, and by default, these models, the S40 RTS are the normal mode models. They are mantle models. They don't have a crustal model. So we push the most accurate crust 2.0 or crust 1.0 over the mantle to get our full model. So the model is fixed to S40 RTS. These are the various parameters which you can choose, try to choose like true, or like if you want to switch off any of them, you just need to say it to be false. So
Okay, so actually, you are allowed to change these parameters. Please don't touch any of the other parameters. But you can play with these ones and don't touch the full gravity because I'm not sure what it does. I think we need to demonstrate it. So, but you can play with oceans, electricity, topography, gravity. You can turn them off or on.
So I think
all you need to do is just to go and type false if you want to turn them off. But don't forget these dots. It must be dot false dot.
So your parameter file is situated in this simulation directory.
Yeah.
Data.
But be careful. If you switch off some of the parameters, then that will affect the quality of your fit, of the fit of your seismographs to observe data. Right now, your parameter file is set such that it tries to capture the full physics. For instance, if you turn off attenuation, your simulations will be faster.
Yeah.
But if you like to see what will happen, go ahead. Okay.
Yeah.
And I can guarantee that the fit to observe data will be much worse when you turn off attenuation. First of all, you will have really large amplitudes in your synthetics, etc. But you can play if you like. But don't submit multiple jobs because we get to keep moving. But if you like, you can play with the parameter file, only this part.
So we have fixed our record length to 25.5. I will suggest everyone not to play with that parameter because that controls the length of the simulations and the time it will take. So yeah.
But later on, if you have access to a supercomputer, you can definitely play with these parameters.
I think these are the most important parameters. You can just, if you have checked, this is another parameter, undo attenuation. Okay, if you are interested in the amplitudes of the seismograms, you should run synthetics with undo attenuation. There are two modes of attenuation like involved in the SpecFM. One takes less time and the other takes more time, but the one that takes more time is more accurate in terms of amplitude. So we have
once you submit the jobs, you will need to wait about 10 minutes. And during that time, we can discuss in detail what is it. But just keep them like this for now.
So we'll be just verifying our run structure so that we have in that next cell. It's done.
And there is one more parameter which is important, absorbing boundaries. You have to set the absorbing boundaries to false for global simulations because there's only one boundary condition for the globe, which is the free surface. But for the one-chunk simulations, you need to control what's happening at the edges of your domain. That's why we recommend you to set the absorbing conditions to true. What happens if you set it to false? You will have some artificial reflected waves from the boundaries, okay? So that's why this is something important. We can discuss all the other parameters once you submit your jobs.
So the next is here. And so these are the binary, like the tools SpecFM gives for doing. So the most important for us, right? We'll be doing that later.
Later, when you submit the job, it will say. There's a script which doesn't we will send you.
Yeah, but it's.
If you want to complete terms, there's the same format. And you will do it.
So we'll use two of the tools. One is the XMesh from 3D, which will create our mesh and save it in the database's MPI directory. And the second will be the XPECFM, which will run the simulation. So here we are doing it. So first I will run the measure. So here, if you look at this command, here change simulation type, this will take care of the say forward, true or false thing. So
think it like this. When we run kernels, we submit forward and adjoint simulations simultaneously. Okay. So first the forward part runs. Of course, we need to check the forward simulations to make measurements. But in this case, we already know, I think. So you run the forward simulations with same forward true, but then integrate the asynchronous simulations. In that case, we have a script which can update the parameter file. So you can find that script.
I think they tolerate change simulation type to 1 and the forward to true. So that's taken into account. So once you run the measure, this will give you the output measured file in the output files directory. And this is the typical look of the output file. So it spits out two important parameters which you need to take care about. So I think Spectrum takes care about, but you need to be mindful. One is the DT. So the DT controls the sampling rate of your seismograms. So it's fixed with that. So you don't like mesh with the DT parameters. Normally when you run simulations, you are careful about the DT. So it takes into account the condition, the DT by DX ratio, what it should be, and it uses that DT. And also it gives you the minimum period where simulations are like accurate. So as you can see, your simulations are accurate up to 46 seconds here or 47 seconds here. So if you make measurements on 20 or 30 seconds with these synthetics, they will not be correct because there will be numerical noise in that regime. But above 50 seconds, you are good to go. Your synthetics are accurate. There are no numerical noise. So you can also save the mesh files and plot them with ParaView. I have just plotted them with predefined mesh. You cannot do this, but this is how the mesh is. So one thing to take care about. So this is the VP plotted. So normally you will see all these heterogeneities pretty clear in the global models, whichever they are published, because they are typically plotted the perturbations. Here we are plotting the exact true velocity, not the perturbation from the frame structure. So you cannot really see the lateral heterogeneity in this mesh. So, but there are heterogeneities which is very small scale in this absolute scale. If you plot perturbations, you can see the heterogeneity in the model. So now I will go to the next, and I will ask everyone to run the solver. So it will take some time to run the entire simulations as we are running. So after you can just submit the solver job, then we can take a pause and everyone can throw questions or let me know if there is any issues. Because this will take some time to spit out the synthetics.
So can everyone run the measure? So in case you have an issue, if it doesn't run, just restart your mode. This is how Carl fixes it. You did it again.
Shut down.
And now he wants to shut down.
But also.
But when you see records on the databases API, this is
You can look at your generated files in this by opening and looking at the file. So they are in the simulations directory. Your simulations are running there. There are the output files.
Oh, can you also submit the folder?
Yeah, I will ask everyone to submit the forward job, then take a break because it will take around 9 to 10 minutes to run it.
Please go ahead and submit the forward simulations. And then we will wait for about 10 minutes to get the size programs. Thank you.
I just restarted the notebook. I just left the card. Yeah, that was.
Yes, it started.
I something catastrophic.
We can answer the question. Just Rıdvan and Masaru, can you hear me?
Yes.
Yeah.
We have a question for you.
Okay.
How would you arrange your computational domain if you would like to use 2 chunks rather than 1 chunk? Do you have any experience?
No, I have never tried to calculate with 2 chunks.
So something that we need to test.
Yeah.
Let's see what really happens. Yes. We have a forum, SpecFun forum, where you can ask your questions. So you can post this question back and we can try to answer it. Maybe someone has already tried. I believe someone tried. But for spoiled global seismologists like me, who wants to run the 2 chunks, which I'm joking. Yeah, sure. No, I'm joking, but you need to test as
Really feels tasting them more great.
No, actually, you should be able to run hardware. This is what I have one shot or
So this 40R uses how does it
That's amazing. Can I just everyone? So here is a great, excellent question. S40RTS is a mental model from Jeroen Ritsema and co-authors, which has Krussel corrections. So the classical mental models constructed based on ray theory involves Krussel corrections. What Krussel corrections mean is that the crust is very thin, but highly heterogeneous. So it's not really possible. The perturbations are too large that the perturbation theory breaks down. So it's not really possible to invert for crust. You need to play a bit. You need to make some tricks. So that's why classical global seismologists or ray-based seismologists, they prefer to apply Krussel corrections. They make 2 assumptions. They say that, okay, first assumption, which is a great assumption, we know the global Krussel model. Okay, there are some good Krussel models, Krus 1.0, 2.0, just they ignore all the uncertainties. And then the second assumption is that they assume that they can estimate the Krussel phase, the phase shift due to crust, using first order approximations, such as great circle approximation, ray theory, etc. And then they estimate the Krussel phase for a chosen global Krussel model, and then subtract that phase from their signal, assuming that the remaining signal is coming only from mantle. And actually, that was, I can tell you that that was my part of my PhD thesis. And that was the motivation why we wanted to do full waveform inversion at the global scale, ignoring Krussel corrections, because which may bias specifically the upper mantle anisotropy, our inference of the upper mantle anisotropy. But then actually the question was about how these models are implemented into spectrum, because any ray-based global tomography model has Krussel correction in the spectrum. So that means they start from 24 kilometers, because the Pram crust is like 24.4 kilometers. So all the models start from 24 kilometers. The upper part is Pram crust, right? Then what we do is we put the 3D crust back because they used crustal corrections. Now to be able to run simulations, some reasonable simulations, we need to put the crust back. And we use crust 2.0 or crust 1.0, whatever crustal model we have. But then there is the challenge. The mantle model starts from 24 kilometers, and this is exactly the question. The mantle starts from 24 kilometers, but now my 3D crust is 7 kilometers underneath the oceans, which can be 70 kilometers in the continents. How do we glue this crust, 3D crust, on top of a mantle model in numerical simulations? And here is the trick. We squeeze or stretch the mantle. So underneath the oceans, we just fill the gap from 7 kilometers to 24 kilometers with the upper mantle values. That's an uncertainty. That's the best we can do because we don't have data in the models, right? And underneath continents, we just stretch the mantle underneath deep cratonic regions, etc. This is how we handle. But if you want to make comparisons to observed data, just keep in mind, there is going to be an effect, specifically on the surface wave propagation. And for this reason, I really would like you to be super careful. If you would like to compare these different mantle models to each other in terms of waveforms, because it's very tempting that there are a lot of mantle models now. You can just run simulations and then make comparisons to observed data and then choose the one which fits the observed data best. Oh, you can say that this model is better than the other one, but be careful. We have to do all these tricks to be able to run the numerical simulations as accurate as possible, but there is always this uncertainty in the upper mantle, which affects the wave propagation, specifically surface waves, but also body waves. And that's why when you make such comparisons, those comparisons may not reflect the quality of the mantle models, but more numerical issues. So just be careful. And actually, because of these issues, we were motivated to run full waveform inversion, adjoint inversions at the global scale, although they are very expensive. And then we simultaneously invert for crust and mantle because now we are using full waveform inversion. We are updating our models iteratively. Okay? And we can start from a 3D background model, which reduces the perturbations. This is how we handle the situation. But that's an excellent question. Just keep in mind, there is this uncertainty in the upper part. Always.
I think my simulations are done. How many have you got the simulation?
Is there anyone who is still waiting for the simulation to be completed? Does everybody have SeisSol numbers under out 553?
Yeah.
Anyone who hasn't?
You can check the files directory. There will be the SAC file.
Is your simulation still running?
Do you run? No veo bien.
That's short period. They only have about 47 seconds. Is what the simulation.
Yeah,
no, I'm sorry, I mean, compared to like, I do like. Oh, yeah, like it was. Okay. But like
I just want to say something about the output solver. It's a pretty good file. While your simulations are running, you can check them and it will tell you.
Oh, okay. So that's all numerical error.
So you can also open the last timestamp file, which will
Yeah.
tell you how much time you need.
Yeah, it prints out at certain, after sometimes, you know, it's 6 minutes more.
Yeah, you see 6 minutes, 45 seconds, 1 minute, 54 seconds, and then.
It gives all those details where you are running. As you have finished, there is no point in checking that right now.
And also, you know, this simulation, the duration of simulations is pretty linear. So if you want to compute 10-minute seismograms, and if it takes, let's say, 5 minutes, that means if you want to compute 20-minute seismograms, it will take 10 minutes. It's very linear. So this is how you can estimate how long your simulations will take before you run the entire simulations, okay? By checking these timestamps. But it would be better to wait a few timestamps because the first a few of them may not be super reliable. But after a few timestamps, you can have a good idea. For instance, you can make a test run for 5-minute seismograms before you run 180-minute seismograms. But you can estimate how long it will take if you want to run longer duration of seismograms. It's linear.
So as you can see, this took around 8 minutes, this simulation took. So now we will have these populated SAC files in the output files, and there will be mesh files in the database of MPI. So,
can everybody see their seismograms?
No, I think we'll run it. So here I am reading the seismograms now. And yeah, I think if your cell 9 runs good, then your seismograms are there. Also, I have read this. Yeah. It's our the origin time. Okay, now the first step of processing our data for adjoint simulation is to make our synthetics and the observed data comparable, because the sampling rate as well as the length of the seismograms are different. So we need to make them consistent so that we can make consistent measurements on them. So that will be the next step. We'll cut and resample our data using OpsPy. So this command will show you the initial. So we also have the BHZ. Normally, this is the downloaded data, or this is the observed data. The broadband channel is named as BHZ. If you can look at the sampling rate, it's 40 Hz because it's a broadband instrument. Whereas our synthetics, the MXZ, has sampling rate of 7.14, which is optimally calculated for the mesh.
It's controlled by the mesh and it's hard-coded.
And we also have provided the 1D synthetics, which we have downloaded from the Strict Movie Global, and you can see they are much more because they are only long period, so they don't really need very low sampling.
So the 1D seismograms you have from Shape Movie, they are computed with normal mode. They are normal mode seismograms. That's why they are computed in a different way with a different sampling rate. So every synthetic seismogram reflects their own method properties. Okay. And this sampling rate in the spectral element code, spectrum codes, explicit time schemes are used, which means you need to be careful with the stability of the simulations. You need to mesh your domain and take care of the spatial and the time samplings together. Make sure that everything conforms current condition. Okay, so that's why for different mesh resolutions, these sampling rates in spectrum, they are hard-coded by trial and error. So you need to be careful. You may, if you would like to increase the accuracy, you should reduce the sampling, time sampling. Or if you would like to speed up a bit, but still making sure that everything is stable, you may still be able to increase the sampling. But everything is hard-coded. It doesn't really allow you, like in the spectrum, you cannot go and immediately change the sampling. Okay. It's super important, one of the most crucial parameters in numerical simulations.
So this part of the code will resample our observed data with the synthetic seismograms. We are not doing anything with the 1D synthetics as they will not be used for our calculation. I think, okay.
Output files are SAC.
Let's submit the adjoint simulations because that will take 15 minutes. Let's go through the parameter file. But you can change it in the parameter file. You can choose ASCII, ASCII, and SAC.
Yeah, I think Spectrum does not miniseed right now. It only SAC and ASDF and ASCII character. So now, after you resample, you can see that the resampling of the VHZ channel is 7.14, so it's now the data are comparable. And as you know, this is the theoretical thing. The observed data is the convolution of the source time function, the response of the Earth, and the instrument response. The GD, so these are the convolutions, and the synthetic data does not have the instrument response, so they are the convolution of the imaginary Earth structure and the imaginary source. So to make them comparable, we need to remove the instrument response from the synthetic data, from the observed data. And so the next step will do that. We will also in this processing step, we will filter our data at the required period bands where we want to see our data. So by default, we have chosen 50 to 100 seconds. You can play with this minimum period and maximum period also. But remember, as I showed earlier with the mesh output files, your simulations are accurate only up to 47 seconds. So you should not go beyond 50 seconds.
And one thing, 47 seconds is a estimated resolution. Don't trust it that much. It's for one radial symmetric prime model with the 3D simulations, 3D models. Just make sure that your filter, even 50 is pushing the limits, but it's okay for the current purpose.
At these periods, the variances no matter are using their sensitivity, will take more sense to involve synthetic with the instrumental response. Should be designed but then if you want to use different just control when before you basically instead of moving the data into the responses control emergency immediately you can either way works. But even if it isn't, why we want to why we this one but you can't run. I hate but then the agents are before you can agents then it's going to be tricky. So maybe so a joint source, but it may not be there. I can move this yeah. Or the next one of the slots. You need to include the instrument response to agents. That's good.
So I think we use the normal instrument response removal routines from OpSpy, and they give these plots as output to show you what is happening. So I think our original data spectrum has all of the entire spectrum, but like we only are interested in this period band of our data. So we just taper our data in the frequency domain in this with this taper function, so that we only get the response at this instrument at this period band, and we also divide the instrument response in spectral domain so that we get the actual synthetics, not any component from the instrument.
Now, I think that is like, you have a session. I think it's got, even what you can do is look in your output folder and see the time.
If you have been able to run the instrument response removal, that's okay. I know.
Yeah. So it is slow. Yeah, I really like, I've never been burned by this estimation program, especially after the first few iterations. Yeah, it's really helpful to just say, this is how long it gives you the time to like. I can go get lunch.
So after you remove the instrument response, you can plot the seismograms, and I think you can see the black and the red ones are observed and synthetics here.
I have a question that you may not want to answer. Why are the 1D synthetics for Terra so much worse than Forge?
So I think it directly with the crust we're using it's the effect of the crust that I think the Terra is there in the ocean. So in the oceanic continent, the oceanic crust, the crust is a lot thicker, and the surface waves are directly influenced by the crustal thickness, and that's why I think the 1D synthetics is worse in case of.
Yeah, here, this is the oceanic path. Remember, the crustal thickness is 7 kilometers. So the surface waves in a 3D model propagates with the mantle waves, whereas in the CRAM, they mainly travel with the crustal waves, which is slower.
Okay.
That causes, I really like that.
Yeah, that's very
illustration, the effect of crust on surface waves.
So that's because shape map uses, or sorry, the Princeton shape movie uses CRAM.
For the 1D, yes.
So it seems like IASP or something would be maybe the opposite.
It's going to be the same because the average crust is about 24 kilometers in all radial symmetrical.
Actually, the 1D synthetics are
always going to be slow.
The 1D synthetics are not results of spectral simulations. They are normal mode synthetics.
Yeah.
And they don't solve the entire wave equation, so they cannot take 3D effects into account. So it's the 1D model.
Yeah. But there is also spectral element seismograms on Shape Movie.
Okay.
So you can download and check. You should see the same effect.
Okay.
And
so I think I will just go forward so that we can submit the adjourned simulation. Then.
Do you know what it's?
What?
The Shape Movie synthetic database for Princeton.
What's it for?
Yeah. What looks like.
Yeah, I think they maintain that if anybody wants to check the synthetics, like as the GCMP is there, so they can also provide the synthetics, see how it's there.
They model stores.
No.
I'm not using for education, but also when I want to work spectral 3D in my computer or something.
Yeah, I think in our seismograms, these are the arrivals, they're the PES, all of them you can see. We are using a 30-minute synthetic, but for the adjoint calculation, we will not use the entire 30-minute window. We will shorten that so that our adjoint simulation does not take much longer. Because due to the implementation of the adjoint simulation, it takes twice as time as the forward simulations because we need to incorporate some at the wave field at certain points, which is stored in the forward simulation. So that makes it a bit longer to calculate the adjoint simulations compared to the forward simulations. So these are the phases you can see.
So the thing is, the adjoint simulations takes longer, a bit longer than twice as the forward simulations, because we are computing the kernels on the fly. Well, actually, it's not exactly on the fly anymore, but if you exclude attenuation, the kernels are calculated on the fly, which means we are repeating the forward simulations and then adjoint simulations and look at their interaction during our numerical simulations. Alternatively, we can store the forward wave field and then run the adjoint wave field and just convolve both two wave fields, right? And in that case, forward and adjoint simulations would take the same amount of time. But the problem is we cannot store the wave fields, okay? Because they are huge files. We cannot dump the entire wave fields in 3D simulations. So that's why we compute them on the fly. That means we need to repeat the forward part of the simulations within the adjoint simulations. So that's why it takes twice.
Yeah.
Simulation duration is twice of the forward simulation.
So this part.
So you store the final wave field to the forward
To
simulation.
initiate the forward part of the adjoint.
You run it backwards in time.
So this step will cut the seismograms to 15 minutes, so that. So one of the things that we do is, like, normally we, for our calculation, we don't keep the east north and vertical component. We change it to radial, transverse, and vertical component for adjoint sort calculation, because if you want to have good S wave sensitivity, you will only use the transverse component. If you want to have P waves or SV waves, you will take the vertical component. So for clean measurements, we will only be using the vertical component today. But normally when it is done, we want to incorporate all of the information we have. So we make measurements in all the components and make our adjoint source.
Remember, your challenge is to compute a clean banana dough. That's why you are going to make measurements on a single component on a single time meter. But actually, you can increase the number of measurements. You can include other phases, and you can include 3 components. And the simulation will cost the same, because the duration of simulations is independent from the number of measurements or number of stations.
These are all the misfit. I think Ibu already told this in the slide. So you can use travel time, amplitudes, or waveform misfit. Our code currently has these 3 ones. So you can try any other type of source, but we will be running it with the travel time source, travel time adjoint source. So
if you want to compute banana, you need to use travel times. But if you like, you can use other adjoint sources.
Also, to just keep it in mind, we have fixed the time window 450 to 570 for Terra station, because we want to capture only the P wave, and we have known that the P wave is coming. The P wave energy is in between 450 to 570. So you can play with the time window. There is the interactive thing you can play, but to get a clean kernel, I think this time window is better if you want to get a clean kernel. So you can see the various adjoint sources plotted in the screen, like they have waveform, the travel time, and the amplitudes. So we'll be going forward with only the travel time. So if you want to play with it, you can play with it, and we'll save it in the next cell, whatever time window you fix. So I have just kept it as 450 to 570. And we also have the second station, the board. So for comparison, in our case, we are making a clean measurements on the Terra station, But I will increase our window length in the workstation so that you can see what the complexity of the waveform does to the kernels. So that's why for the Borg, the time window is a bit longer, 430 to 700 seconds. It has all the phases incorporated. Most of the, whichever is coming in that. So you can already see the adjoint wave, the adjoint source, they are not a single wiggle, they are complicated wiggles, and it will complicate our adjoint kernels also.
Yeah, you can see that there are multiple arrivals within your time window. Yeah, right here.
One of this is the P arrival, there is the depth phase PP coming, there is the PCP, the core reflected phases, as well as the PP, the surface reflected phases coming at the same at this window length. You will see which are the phases. So the next step is to write out the adjoint sources. So this code will do it. So SpecFem can read ASCII adjoint source files. So we just write it as an ASCII adjoint source, and we need to save it to a different directory called the SEM directory, which we need to create before running the adjoint simulation. And we are saving our adjoint sources. So as you can see, as I told that we will be only using the vertical component. So we are using 0. The adjoint source is 0 for the other components, the radial and the transverse component. Only there will be adjoint source for the vertical component.
Even if you don't make any measurements on the other components, SpecFem still wants to see 3 component adjoint source. Okay, so that's why even if you don't make any measurements on the horizontals, you just provide a 0 file for the other components. Okay, otherwise SpecFem will complain.
If anyone wants to play, like look at the adjoint sources from all the components, you can change it here. You can put it T or write all. So as accordingly, if you want to do it, else we'll go forward with the vertical component. So once it is written, the next part will be modifying the parameter file as shown earlier. 1, the simulation type should be changed to 3, and we don't need to save the forward wave field again. So we can change it to false.
So that's the recipe. For the forward simulations, set the simulation type to 1, save forward to true, to save the last frame. If you just want to run synthetic seismograms, you don't need to save forward the last frame. You can also set it to false. But if you are going to run adjoint simulations, it has to be true. The last frame must be stored. Then, once you have completed the forward part, just before you submit the adjoint simulations, you set simulation type to 3. 3 means now I'm running adjoint simulations. And to edit the parameter file, you have a script. We do it automatically with the scripts.
So this is the script, the change simulation type minus B.
Yeah,
this will
change simulation type.
This will again fix those, and I think we can now submit the SpecFem. As you know, we don't need to run the mesh again because the mesh is saved already, so we can already run the SpecFem.
And now you can submit your adjoint.
And it will take around 12 minutes. So if there is any more question, even.
Yeah, once you submit, you can monitor the status of your simulations by looking at the timestamps stored in the output files directory. Then you can understand how long we should wait. Okay.
Do you think my forward run finished, but it took 23 minutes? Do you think that that's like a bad node, or it's kind of surprisingly different?
Okay, can be.
How long is everyone else's run?
10 minutes.
Is there anyone else whose forward simulation took longer than 10 minutes?
Me? Yeah, we just need the bad notes to instruct us.
Well, it used,
Can be a bad note.
clusters where it's highly variable because people are.
Can be a bad note or something, or if you have multiple runs.
Same thing.
You are running one. We didn't change the resolution. And this is for adjoint.
48 minutes.
Okay. Can I?
So say now. 48 hours.
Okay, Carl is going to see here tonight.
I think the first iteration gives absurd values. The first iteration gives absurd values for the adjoint simulation.
Just look at it. But 48 hours is already bad news. No, that might be more issue. And actually, let's report this to you.
So I think it will run for 18 minutes.
That's pretty good. Yeah.
So we can take your questions now while we're looking for your age of simulations.
You're just 12? So here we all I changed is the table. Yeah.
I lost the connection. So
I think it's just that. Yeah, I guess I could. It was fine. I know what fine is cosine. I don't know what cosine is. But I should. Yeah. What does cosine mean?
it's type of filter.
How is it different from cosine?
I have a connection problem with
The actual code Oh. So.
Your job is cancelled. You can submit a new job. I think most of the simulation.
There's no cosine.
When do you run?
No.
But I think it's because I start when Professor Ebro started to her presentation.
Okay.
So I already submit the job. So probably I went out of time. Run out of time. Yeah, it's okay. Thank you.
So just to be clarified, if somebody has started their job early, the note booking is only for 2 hours. So after 2 hours, your job may be.
But it wasn't 2 hours, right?
You need to resubmit your job if you have.
It's just like a phase. But it's literally the same. So it's like how. Yeah. Okay. So, yeah. Yeah. So that's cosine, which means it's going to be. So like cosine power. Well, actually, cosine of the power of infinity would be a delta wherever it hits one. So actually, that might make it less sharp right there. Right. Or yeah, it should make it so that the peak is sharper, but the size. Yeah. Just a lot of working. I just, when I want to visualize like a function really fast, but I'll just use the website. I used to know how to use like the coding. Yeah, this is just like the fastest way to like plot stuff. Or if you want like, I use a lot of like getting at the simple distance. I think it will work. Yeah, I was just but I don't think again this website's. You put it in the pen. There you go. Oh, yeah. So the classic. But it also used the design. Does that matter when you're doing a paper? Well, let's see what the formula was for the cosine paper. Is that should be non-negative as well. They might be being careful with that, make sure that you're picking a period or like, the half period where it's positive. Yeah.
Yeah. Because what is, I always forget it, cosine of pi over 2.
That's 0. Yeah.
So
You're gonna wanna get picked from negative pi over 2 to positive.
why can't you use a sine?
Oh, I mean, if you use the sine, there's a different phase, it would be equal to cosine. With this phase, right?
Like a hyperbolic.
Even that.
What is it?
I don't know if hyperbolic.
I can't. Well, I'm sorry.
So since you are waiting for adjoint simulations, let me show something.
It's a bug.
Well, yeah, but like, so if you take out like the cosine, right, that's a smooth function. But if you take the ends.
Okay, so just a bit of information about the adjoint tomography workflow. So one question is, what are we going to do with what we are calculating right now? What are these kernels? Why do we do this? Okay. So if you look at the adjoint tomography workflow, basically we have 3 main stages. So anything denoted by blue, they are the numerical simulations, forward and the adjoint. Then we have pre-processing part, which you just did to compute the adjoint sources. And then we have the post-processing part, which we are not discussing, but actually Brian went through this part yesterday with the SeisSol. This is what, not SeisSol, sorry, SeisFlow does. Okay, so first, at the beginning, we download data, observed data, and then we compute the corresponding synthetic seismograms, right? Once we have observed and synthetic seismograms, this is just what you did. You just make them comparable to each other. You process them, you resample them, you cut them, you window them, you filter them. You remove the instrument response and make them comparable to each other. And then you compute adjoint sources. Until here, it's the data pre-processing part. Once you have the adjoint sources, then you initiate the adjoint simulations, which you just did, right? Then what is the output? At the end of the adjoint simulations, you will get these kernels, adjoint kernels, which are nothing else but the gradient of your misfit function. So, gradient of misfit function, if you have the second derivative of your misfit function with respect to model parameters, you will have the Hessian kernel. And if you have Hessian, and if you have the gradient, then you can use a Gauss-Newton method to update your model, which is commonly used, especially for ray-based tomography problems, right? But we cannot calculate the second derivative, we only have the gradient. So we need to use a gradient-based optimization technique to update our model. So right now you are running one banana donut, but you can go ahead and select more phases on 3 components, on multiple stations, and assume that you can select 500 earthquakes for your study region, and you can make the same measurements and compute the kernels for all these events, all these measurements. So basically, we run simulations per earthquake. So the result of every simulation per event gives you an event kernel, which is just a simple summation of all these banana donuts. Okay? And then the result will be event kernels for multiple earthquakes. Then the first thing we do is to sum them up to get one gradient file. It's the gradient of the misfit function, nothing else. You can call adjoint kernels, you can call Fresher derivatives, nothing else but the kernels, the gradient, which tells you in which direction you need to update your model. Okay. So then we have some data processing parts again, what we call post-processing. We have the gradient, then we sum the kernels, we sum them, and then we apply some processing, we precondition and smooth the gradient to remove some inaccuracies coming from numerical simulations. Or sometimes we also use this step, preconditioning, to speed up the convergence, okay? And then once we know, I mean, gradient tells us in which direction we will update the model. But we also need to know how much we need to perturb the starting model, right? So this is what we call line search. We just randomly perturb or choose some perturbations for our gradient, and then make some tests, run some simulations, and compare them to observed data, and look at the model, the perturbations that would give us the minimum misfit. Once we determine the step length, then we update the model. That update is, if you are using a steepest descent method, that update will be, you have your starting model that you use to compute the kernels. Then you will take the minus of your gradient and multiply with the step length and add it to your starting model. This is how you update the model. And the first iteration is always steepest descent. This is how you update. Then you have a new model. For instance, M1 equals to M0 plus minus of your gradient times a constant, a step length. Now you have an updated model. This is where we use these kernels that you are just computing. Okay, then we look at, is our model converge? Is it the final model that we want to have? If your answer is yes, then stop it. That's your model. Now you've updated your model and you are good to go. Go and publish your model. If not, then go back and then recalculate statistics this time using the updated model. And then repeat the same steps again, but this time using the updated model to compute your synthetic seismograms and the dynamics. Go through the same steps. At the end, update your model using the gradient, and then if you are happy, go and publish it. If not, repeat it. Yeah.
So when you say the model, you mean the velocity construction model, or you mean both the velocity model and the when you updating the model, you mean updating both the simulation model as well as the velocity model, or you mean just the velocity model?
Well, this model is what we use in our simulations. But it doesn't only take into the velocity model. It can answer and also what we mean by velocity. We can use velocity, SOA velocity, source parameters, and attenuation to elastic attenuation model. Or we may also like to include we can use and depends on your choice, depends on your parameters. And yes, update means whichever parameters you chose to update. This is what this is what you need to decide at the beginning of your model.
So can we do this, like we keep the model or anything, with anything with the path or size and the probability constant, and just work on the perfect source and then just update it when you have a lot of.
I understand your question. To be able to run numerical simulations, you need to provide POA model, SOA model, density model, at least minimum. You need to find these three parameters. But you may choose to update on the SOAs. And your solver will always want to see here and density as well. So that you can keep that fixed. And you can only update the SOA. But remember,
simulations with only S-wave model or only P-wave model. At least three parameters. And instead of P-wave, S-wave, you may also choose to ignore shear modulus and kappa modulus. The parameterization is up to you, but you know the relations between kappa modulus, shear modulus, and S-wave. So it's all. So parameterization is really important, and this way you ask maybe how are your simulations going?
I think they're
Almost done. Probably they are still running. Have you completed? Do you have your kernels? Okay, then let's go ahead. Then maybe if you have time, we can discuss the parameterization part of the project.
The timestamp for the adjoint simulation is timestamp by word and adjoint.
Yeah. So you are still running.
Yeah.
How many people are still waiting for the simulations? 1, 2, 3, 4. Okay, let's wait 5 more minutes. Can you check how much time? 4 minutes. Okay, let's wait 5 minutes. Then we can continue. I think we need to wait 48 hours for Carl. 18. Okay. So meanwhile, maybe I can, for 5 minutes. So for instance, this is something that you need to decide before you start your inversion, okay? Parameterization. This is something that you decide based on the physics, your data, what physical parameters you would like to address, etc. So, for instance, this is just one example. You may write your gradient in terms of the perturbations in density, shear modulus, and bulk modulus. Okay. Instead, I can also use the perturbations in Vs, Vp, rather than shear modulus and bulk sum. It's up to me. Or for instance, what we like to do is instead of using S wave and P wave speeds together, we like to because you know both P wave and S wave, they have the shear modulus. They depend on, and there's this trade-off over the shear modulus. Then we like to parameterize like S wave speed and bulk sound speed. Bulk sound speed is square root of kappa divided by density. And the shear wave speed is for isotropic medium. Square root of shear modulus divided density. At least there is no trade-off due to shear modulus between them. So you can define your parameterization how you like. For instance, if you would like to solve the source parameters, all you need to do is just to go there and add one more summation and add the perturbations in source. Now I'm going to add perturbations in Q, shear attenuation. That's perfectly fine. Mathematically, there is nothing wrong. But in practice, you need to test. That brings us to uncertainty and resolution analysis. But this is perfectly fine. But then right now you are running, yes, you include attenuation in your simulations, but the kernels you are computing will be for elastic parameters, like P wave speed, S wave speed, density, they will be all elastic parameters. So one question yesterday was, how can we compute the kernels for anelasticity attenuation model that we may also like to update the attenuation Q model in simulation. It's like this. You don't need to change anything in the solver. What we do is, if you look at Trump et al. 2005. It's also described there. All you can look at. I also revised it in Bosda et al. 2011. So if you use the relation between the shear modulus, frequency-dependent shear modulus, and the shear Q, this is the relation between them. Assuming that Q is constant over the seismic period band. This is not for frequency-dependent Q. We just assume that Q is constant over the frequency, seismic frequency band. Then this is the relation between the perturbations in frequency-dependent shear modulus and Q, perturbations in shear Q, where mu omega 0 is the shear modulus at the reference frequency, and then you have these 2 divided by pi, ln omega is the frequency band divided by the reference frequency and this signal function, which is nothing else but the first term, this ln term, logarithmic term. You know, the Q has 2 components. One component is responsible for the amplitude variations, and the other component is responsible for the phase shift, physical dispersion. So this logarithmic part is responsible for the physical dispersion term, and the signal function is responsible for the amplitude. If you go and insert this into Born approximation in the derivations, you can come up with an expression like this. So basically, this tells us that you don't need to change anything in the solver, but just go ahead and then calculate your adjoint source. Let's say travel time adjoint source, like what you did right now. Calculate your adjoint source for the elastic adjoint source, and then take its Hilbert transform, which is coming from this relation. And if you apply this transformation to the elastic adjoint source, then it will give you the unelastic adjoint source. And now, if you use this in the adjoint to initiate the adjoint simulations, and then look at your shear modulus kernel, mu kernel, that will give you the Q kernel. So the mu kernel will be the Q kernel. This is the trick we play right now, okay? But it's just the Hilbert transform of your elastic adjoint source, basically, that transformation. So that means if you want to perform an inelastic waveform inversion, you need to run 2 adjoint simulations. One for, here, one for the elastic parameters. If you want to simultaneously invert elastic and unelastic parameters, you first need to calculate the elastic adjoint source and run elastic kernels. And then you should make this transformation and then rerun the adjoint simulations with the unelastic adjoint source. So the first line is the travel time misfit. The elastic and unelastic kernels you would have for a travel time kernel. For instance, for a S-wave, travel time misfit gives you a banana donut, right? However, the unelastic one is not banana donut anymore. You see the middle part it's more like an amplitude kernel.
And in both cases, you have, you can use the same misfit function?
Yes, you will use the same misfit function, but you will just make this transformation to your elastic adjoint source to get the unelastic one. Okay? So then you need to run 2 adjoint simulations, and your total misfit would be the summation. I mean, of course, unelasticity and also elasticity also affects the amplitudes. Then you can also calculate amplitude kernels. Then your total misfit would be the misfit at the elastic misfit for the elastic part from the travel time measurements, and elastic misfit from amplitude measurements, plus unelastic ones. So basically, in the end, to have the total gradient, you sum all of them.
So you can sum up different gradients based on different misfit.
Exactly.
evaluation. So you don't have to stick with one single misfit.
Well, you can, it's up to you.
Okay.
But if you would like to simultaneously update elastic and unelastic parameters, this is what you do. Then your total misfit becomes the summation of all these individual misfits. But then you may say that there is going to be trade-off between these parameters. So you may also choose to, for instance, first fix the elastic part and only invert for the elastic parameters. And then in the next iteration, you can fix the elastic part and only invert for the unelastic parameters. So it's up to you.
How related to that question, like how consistent are like the final models if I pick different misfit functions? That's my question. Like, if they are too different, are they consistent each other?
Well, if everything is implemented properly, for instance, think about phase measurements. Either you use travel time misfit or instantaneous phase or double difference travel times or multi-taper travel time. They are all phase misfits, right? So ultimately, if everything is implemented properly, they should all be minimizing the phase. So ultimately, you should get the same answer. But it may not be the case for different reasons. First of all, I think when you change the misfit functions, the main effect is you should observe it will be on the convergence rate. Some of the misfit functions may converge faster, and this is desirable. But second, there is the non-linearity of the problem. Sometimes, actually our goal is the optimization part is a bit more tricky. Not that straightforward. That's why you need to understand every step. You may get stuck in local minimum, not the global minimum. So especially this is something you may observe when you use L2 norm waveforms, because actually that's one of the main reasons why we still prefer phase measurements or separate phase and amplitude from each other, because phase is more robust or more linearly related to the model parameters. So, but if you immediately start using waveform misfit, you may get stuck. You may get a quick answer, but you may get stuck in a local minimum. So actually, there's a huge literature on the choice of misfit functions. So you need to choose one of them according to your problem. And maybe I should dedicate a separate lecture on the choice of misfit functions, because there are really interesting things. For instance, we also combine different misfit functions when we update, and they work pretty well, such as we combine double difference travel times with classical travel times, and even we use a variant of instantaneous phase, exponentiated phase, or we define the double difference version of the exponentiated phase, depending on your problem. As long as you know what you do, it should just change the speed of convergence. Or some misfit functions will give you more detailed structure. Because, for instance, classical cross-correlation travel times are really robust. We love them. But you are just highlighting the maximum amplitude signals, because when you take cross-correlation of two signals, it just highlights the time shift of the maximum amplitude part, right? So that means you are kind of suppressing the scattered waves. But the scattered waves can be extremely valuable when you are imaging the plumes, because there is a well-known problem with the travel time measurements, which is called wavefront healing, that you observe when you are imaging the plumes. You need scattered waves. So then instantaneous phase provides a better alternative. There are papers like that, for instance. We can talk forever on this. Is everybody okay now? Everybody has the kernels? Now we have that, then we are at the most exciting part. You are going to visualize them.
If you run this cell,
Should they kill?
no, not, they should run the last
Oh,
cell,
okay.
this one.
Yeah, please run the last cell, then they will kill, right?
Yeah. It is
So-
done, you need to again go to the terminal.
So now we run the simulations on multiple nodes, on multiple cores, right? So then that's why you have multiple output files. So basically, if you look at the output files directory, you will have multiple files for each parameter, the number of processors you use during the simulations. So actually, that means your model is now split on different nodes. You need to combine them in a single file. This is what you do now.
Okay, so I think if you have done that cell now, I think you need to go to the terminal. Maybe your connection has been disconnected. You need to again SSH into the system. You need your password and the token again.
Is it how it should be, or did it just happen to you?
Mine turned out to.
What also could happen is I submit the notebook as soon as you started your lecture. So I run out of time, so I have to resubmit again. So that could
Because
happen.
there's a wall time.
Yeah, so the problem, this is the problem with SSH. They may timed out, the SSH connection timed out, and you need to reconnect to the frontend machine again in the terminal. And again, you need to switch to the scratch directory. And you need to go to the workshop directory. And now if you look at the status of your job, yeah, it's still running. The Jupyter job is still running. We will cancel this job so that we can start the visualization job. One thing I like to say that wherever your notebooks are open, please don't press the reload button. You will be able to visualize the notebook even if you like kill the job. So don't reload that browser page. So I will just cancel it. With this command, you can also, whoever is done with the adjoint simulation and the last cell, the compilation part in one single file, they can cancel. Now if you check, yeah, it's canceling. If you see the status is CG, it's canceling. I think you can submit the new job, that DCV. There should be a script called as job.dcv. I think you should also need to use the partition.
So if you were not logged out, I think you need to kill your job before you submit a second job for visualization. But if you are logged out, I think in any case you should, yeah? Because even if you are logged out, your job might still be running. So just check, if you have a running job, kill it, and then submit another job for visualization.
But I can.
You want to?
No. Yeah, you should change the job.dcv now.
Okay, you are changing the job. I mean, you submit a job, new job, but be careful, you change the name of the job. For visualization. So kill the existing jobs you have been running, and then submit another job. Yeah, this one, which is job.dcv.
If that's running, you will get the DCV server. dot out. You need to connect to this link.
Can you just click on this link?
We have to use your username again. Now I think you are connected to the interactive desktop as you were in the morning. This is the same kind of setup.
Yeah, you open this window. Oh, yeah. You still have a heater?
I did.
Oh, you did?
So has everyone is okay with opening this screen? You can tell DCV server.out. DVC server. DCV.
So can everyone open this terminal? Who couldn't? Yeah. You never?
The simulation is not the entire. So, what we do is, for instance, right now the Google says no, but we or I don't know how.
Sí, no, el mundo de la por lo que yo estoy dando y el original. Pero es que yo el problema es realmente complejo también. Para romano, hasta barra romano, no, método urbano. Se me quedó la siempre veía a la Andrea ficcional. Yo de tomografía yo no sé mucho. Yo me preocupo de las fuentes. No nos preocupamos de las fuentes, no estamos por conocidos.
Y obtienes las fuentes con el modelo.
Es todo circular. Ellos asumen que conocen las fuentes para obtener el modelo, pero nosotros también asumimos para calcular las fuentes. Exacto, no, pero bueno, depende de la escala, porque por lo que yo supongo, las soluciones de momento que simulan son regionales, con estaciones cercanas y con eso se extrapolan a estaciones más lejos.
Estos son de
So can everyone, does everybody have this? Not yet? Don't help us, help the others. Yes, you should help the
You have to do this stuff. So like in back in your terminal window, you want to follow this stuff. You'll launch like a VNC.
This file yet, but eventually you'll have it. You run cat DCG server out.
If you are here, there will be one script called run visualization.sh. You can just run it.
And then log in, get a terminal. /1. Yeah, me too. Everything I do is.
It will open Paraview and you can visualize your kernels. Take some time.
I was looking at like a deep of it.
These are the calculated kernels you have practiced.
Straight out. I did not get that error. If you drop. Yeah. Yeah, and then now, so there's, look for this file, does that file exist? Because that's how you get the computer. Just like a file or cat. File job. And then DCD server. And then copy that. I'm tired. Yeah. Don't worry. So this should, you just log in and you'll get like a tap. Yeah. You only have one more step. So. And then from this terminal, there's a script you run. It's like called run visualization. Yep.
So I think the updated instruction for submitting the visualization job is in the GitHub repo, not the notebook. Yes. You should point to the GitHub repo again, and there is the updated code how to run the HPAC.
Yeah, we'll launch Paraview. Not sure what it is. And you'll see right away once it loads. Just might take a second. There you go.
Banana donuts. That's it, yeah.
So did you see the real life from there, or you copy the parts and you look at the
Yeah, if you ever encounter, I probably do this, the computer I use doesn't have this fancy stuff, so I copy the files.
Oh,
It takes forever.
Oil, can you journal?
So once you are done with the kernels, maybe I would like to point out some.
Can everybody plug this? How many of you could plug the kernel?
You got a kernel.
Like a kernel?
So if you can see, one of the kernels is really clean one. This one is the Terra station. And here we have only chosen the P wave, the P signal. That's why you are getting a clean kernel. But in the workstation, we used a longer window where there were like effects from all of these phases. If you go to open the notebook again at the.
So remember, you use two different types of time window length. One of them was capturing just the P wave, the other one was capturing a longer duration, other phases as well, right?
So you can see
all these phases.
One has this PP, there is the PCP, and you will see that the kernels are very strong PP signal because some of the PP amplitudes are moved. And you can see in the kernels there are some sensitivity in the core which is coming from the PCP phase. So that's
also because we have larger perturbations in the upper part. So that's why the PP perturbations are always larger than PCP. Not always, but typically.
So this is the PP sensitivity. There is some PCP sensitivity coming in that station.
Now one question. Is this a clean banana donut now? This one. Is it?
It's not perfect. No, it's okay. Yeah,
It's okay. It looks like banana donut, but it's not perfect. Why? I say it's not perfect because this is 0 and the middle part is not 0. Why? Yeah.
You use multiple frequencies.
That should be fine because the other kernels are also not, the measurements were not made at a single frequency. In the other kernels actually. They were the 9-20 seconds, they were just the minimum period, not much. Okay. It was very long frequencies because we cannot, yeah. That's not the reason. When we face this together, there's one time difference. Yeah, because this is a shallow line and at 50 degrees, direct P wave and the depth phase, small PP, they are coming almost at the same time, so their sensitivities are interfering with each other, so multiple phases. But there is one more reason. Remember what I told you, if you want to have a clean banana donut, it's a radially symmetric curve model. You computed these kernels for a 3D curve. That's another computation. But does it matter? So should we just discard, for instance, this one, this kernel? Should we or not? I mean, what does it mean? Should we always have clean banana donut kernel? If you are using ray-based methods, you don't have these kernels anyway, but yes, you should. But if you are using ray-based methods, yes, because you need to isolate every phase. But in this case, in the full waveform inversion, it doesn't matter. Actually, we don't care which wiggle we select, what we do. This is perfect. You just update the model according to your kernel.
I was wondering about your misfit function that you use is the travel time one. And you have this alternating slow fast.
So
it's not constrained at that point, right?
Well, you cannot constrain it one molecule. That's why we need cross paths and multiple stations and multiple earthquakes. So yes, you cannot update your model properly with a single measurement. But assume that you will have all these measurements from other paths. And eventually this is the logical seismic tomography. Then everything should be solved.
Then I have another question, sorry. So you said you sum the kernels, but do you not, like, should you not really sum an average? Because what if you have like one really bad data?
And then actually, then you need to be careful. You need to exclude all the bad. So that's the challenge. That's something that we need to do. If you would like to do seismic tomography, either away from the earth or crystal, you have to make sure that there is no bad measurement. But yes, if you have a bad measurement, it will spoil your grade. So that's why, in the ideal case, you can run this full waveform inversion workflow in an automated way. In the exploration side, this is what they do. They just initiate these inversion iterations. They perform 500 iterations or maybe thousands of iterations without looking at anything. Ideally, we should be able to do something like this, but no. Because we are still trying to discover something in data, and then there may be some bad measurements, etc. So we still need a seismologist. It's not something that an AI can do. Or maybe we should take the challenge and see what an AI can come up with the model. But you know, you really need to know what you are doing. So that's why it's not just an automated workflow. You still need to use your seismological intuition, because there are lots of subjective decisions you need to make. What your missing function will be, how will you parameterize your model, how much are you going to smooth the gradient, or what precondition are you need? You know, lots of different factors that still you need to make a decision, and you know, you need to understand your data. So that's why any seismic tomography must know data. All the data challenges, because real data has real problems. And I'm doing physics. Right. So these still need seismologists, I can still be sometime.
Just a reminder, your allocation in frontier will end at 4 p.m. So after 4 p.m. you may not be able to see it. We are almost close to the time.
But maybe what we can do, you know, we can provide this model file to all the workshop participants. If you cannot plug it now, you can plug it later on with Parallel. All you need to do is just to read the model on your own local desktop.
Can we install Parallel?
Yeah, you need to install Parallel. It's a free code you can install, and then plug and play with the model kernel, on your own local computers, okay?
So has anyone tried any other frequency band other than 50 to 100? Yeah, you can see that the shape of the kernel will be different.
Yeah, I use 60 to 80, and it's
Much
a bit
cleaner.
fatter, yeah.
Yeah. And we have, well, you see, you ever got, it's 60 to what?
60 to 80 seconds.
60 to 80, looks like it's going to be, I don't know if you also changed your measurement window, but.
A little bit.
Yeah, it's mainly keyway. One more question, sorry. Can you show the keyway, the other calculation? So if you look at the Jupyter notebooks, on one side, Tara is the color is red. Yeah, this one. But the other one is blue. Why? Why do we have two different colors in different paths? What does the color tell you?
Yeah, one thing to get, these are made with clear P window, so both are P kernels. One is for Tara and one is for work.
So you have a red kernel. Red means, what does, okay, let me tell you one thing. So if you have red color, this is your gradient. So when you add it to the model, you are going to take the minus of this, okay? Red is negative. When I take it minus, it will be positive, and I will add something positive to my model, which means my velocity will speed up. So negative kernel will speed up my model. Is it the case? Can you show the corresponding synthetics for this kernel? Not work, I think it's character. Yeah. Are they? So you can understand if you have the correct sign. So for Tara, you see the synthetics are delayed. The red ones, they arrive late. So that means I need a faster wave speed model to match the observed data. And that negative kernel tells you that. Because when you add it to the model, you will take the minus of that, which will be positive, and it will speed up the model when you add it to the model. And this is what I need. So this is how you can verify if you calculated the correct kernel. But on the other path, you have a blue positive kernel, which means if you look at data, it's a bit difficult to see, but you see the synthetics are arriving earlier than the observed, slightly. That means you need to slow down your starting model. That's why you have a blue kernel. So basically, the sign of the kernel is controlled by your measurements, travel time measurements. Okay. So that's why on one path you have negative kernels, on the other one positive, which is directly controlled by the travel times. And this is what we want. This is how you want to update the models, right? But again, you cannot update your models with two stations, two measurements. In seismic tomography, assume you have all the stations, all the earthquakes. You need to do these measurements for all the time windows, and then optimization techniques should just sort out what the best model should be. Okay. Any last question? You are the last. Felix.
So I'm just curious, trying to think in another tomography methods when they have checkboard tests for checking this, how your station distribution may affect your resolution. How do you perform those tests based on the sources and the stations you may have? So how much you can
should perform the same number of iterations. If you want to do a regular checkerboard test. So the question is, it's very common to perform checkerboard tests. So you can choose a checkerboard as a target model. And then with your source receiver configuration, you can try to invert with the data and then see if you are able to, how well you can recover the checkerboard, okay? With this type of optimization, in the full waveform inversion, if you want to perform a regular checkerboard, you have to perform the same amount of iterations, exactly in the same way, which is going to be costly.
Yeah.
Alternatively, what we do is we perform point spread function tests. Point spread function tests, PSF tests. If you look at Fichtner and Tramper 2011 papers, so what we do is, in your final model, if you would like to analyze any region of interest, let's say you want to analyze the resolution of the subduction along the Hellenic arc, you just go and put a Gaussian perturbation in that model. You perturb that region a bit, like 2%, 3%, and then calculate the gradient. And you also have the gradient for the non-perturbed model. So you have two gradients, one with the perturbed, one with the non-perturbed. And the difference between these two gradients should give you the Gaussian perturbations you include. If you can retrieve the Gaussian perturbation, you can say, oh, okay, my data coverage is good enough to resolve this feature here. If not, you will have smearing, and you can also see the trade-off, leakage to the other parameters, and then you can assess the quality of the trade-off between parameters like that. So this is what we do, and it costs one iteration. But then the disadvantage is that you need to repeat one iteration for every region of interest. There are other techniques as well. Maybe you can ask Cash. He wants to take this challenge. How we can make a better uncertainty quantification for full waveform inversion. The bottleneck is that everything is expensive. So how can we optimize the problem while we can still comment on the resolution and uncertainty in our modeling techniques? What was your question, Cash?
Oh, I was gonna ask, the Earth doesn't look like banana donuts, probably, right?
No.
So why don't we do have an explicit regularizing term for these sorts of inversions?
But we are not updating the Earth as a banana donut. These banana donuts just, they just show you how your seismic waves are affected by the heterogeneities inside the Earth. And this is the rate path of your seismic waves. Yeah. And it doesn't have to be this, because for surface waves, they are just sensitive to the upper part, etc. So parameterization is a different problem. Banana donuts are different. Banana donuts are just the data sensitive. They just show how your seismic waves sense the lateral heterogeneities and the radial heterogeneities.
So the regularization is done with the parameterization?
Parameterization, and also we can apply some regularizations to the computed gradient, like smoothing or preconditioning, etc. Parameterization is different. For instance, right now, global seismologists or geophysicists, they like to use, for instance, spherical harmonics in the horizontal direction or some splines in the radial directions. Some like to use these global basis functions. Some like to use local basis functions. What we do, we just use the mesh that we use for the spectral elements, but then it gives us excessive number of model parameters that we cannot really resolve. Then we smooth them, etc. So that's another issue. Regularization comes after the computation of these banana donuts or the gradient in general. Okay? That's another problem. I can recommend some papers to you. You can read on the consequences of the chosen parameterizations. Any other question? Yeah.
How long can this period go to super long so that you have even normal mode, like very low frequency?
That's a great question. Carl is smiling.
I think it's like either coming out of DJI or.
So right now, and actually, if you remember, there was a parameter in the par file, full gravity. I told you keep it false. I don't know what it's currently doing. So in the current version, or in the Spectrum 3D globe versions up to now, we only had the self-gravity was based on Cowling approximation, which doesn't allow us to compute the normal modes. because Cowling approximation is good enough up to 250, 300 seconds based on personal communication with Dimitri Komatic. And so that's why our upper limit is around 250 seconds. We don't look anything longer. But if you want to compute the normal modes numerically, and which is which has been the dream of Jeroen Tromp for a very long time, because then you don't need all these super hard theory, normal mode theory anymore. Together with actually the Homnat Garti from Queen's University, he is working on this problem. He implemented full gravity using, what was it, infinite spectral elements to be able to solve the Poisson equation. So he did a trick. But there are two challenges. Actually, in theory, he solved the problem with these infinite spectral elements. But the challenge is, now with the full gravity, you can look at normal mode frequency spectrum. But the challenge with the numerical methods is the time step, because now you need to run longer simulations, right? Longer duration of seismograms, like a month, 1 month's duration of simulations to be able to see all these normal modes, right? But then that means you need to decrease your time step in a way that you will be able to run such long seismograms, which is a super challenging numerical problem. So it depends how we optimize this. But now in theory, with the new version of SPECPAM, created by Homnat Garti, it's possible. In principle, you can take the full gravity into account. And since they added this parameter, full gravity option in the par file, I think they are merging these two versions. But I'm not sure. I mean, you need to test if you would like to run such long duration simulations, because then you may optimize the problem. Because since you are interested in long wavelengths, you may not need such high resolution simulations. But you should still be careful, because you cannot really decrease the resolution of simulations arbitrarily. For instance, right now we are using a mesh with 96 spectral elements on one side. Normally, we never run such simulations for global simulations. Why? Because you need to have enough spectral elements to make sure that you capture the spheroidal shape of the planet. Otherwise, you will start having kinks which can affect surface wave propagation. But maybe for normal modes, you can go with it.
How many elements do you use?
Technically,
we are done.
We have a poster session.
Okay. So thanks very much for joining. We would be happy to answer your questions later on as well. And now we have the poster session. If you would like to discuss, we are here.
Listening still?
Masaru and Ridwan, are you still there?
Yeah, of course. Yeah.
Let's clap for those guys.
Yeah.
Thank you, everybody.
Thanks very much. Actually, all these notebooks were created by Masaru, Oyon, and Ridwan. So thanks very much. I just came. Yeah, Masaru did most of the work with the notebooks. Ridwan provided the insight, and Oyon took the challenge to guide all the practicals. I just came here to talk. So thanks very much.
Thank you.
So are we ending the online session?
I think so, yeah.
Okay, so thanks very much for joining the session online. See you tomorrow. You can just like.